Hello, everyone, and welcome to our workshop on integrated nuclear renewable energy systems. I am Hossam Kishawy, Dean of Engineering at Ontario Tech University and the Liaison Officer of the IAEA Collaborating Centre at Ontario Tech. Our workshop today is online, and I hope in the future we will have it in person. But I have a confession to make today. Looking through my window here in Toronto, it is really cold and rainy, so we don't miss much of being online. Now, I would like to give the floor to our Vice President, Research and Innovation at Ontario Tech University, Dr. Les Jacob, to deliver the land acknowledgement. Please, Les, the floor is yours.
Thank you, Hossam. Good morning, everyone. My name is Les Jacobs. I'm the Vice President, Research and Innovation at Ontario Tech University and the Director of the IAEA Collaborating Centre at Ontario Tech. Welcome to our two-day workshop on integrated nuclear renewable energy systems. I'd like to start with our land acknowledgement. Ontario Tech University acknowledges the lands and peoples of the Mississaugas of Scugog Island First Nation. We are thankful to be welcomed on these lands in friendship. The lands we are situated on are covered under the Williams Treaties and the traditional territories of the Mississaugas, a branch of the Greater Anishinaabe Nation, including the Algonquin, Ojibwe, Ottawa, and Potawatomi. These lands remain home to a number of Indigenous nations and people. We acknowledge this land out of respect for the Indigenous nations who have cared for Turtle Island, also called North America, from before the arrival of settler peoples until this day. Most importantly, we remember the history of these lands has been tainted by poor treatment and a lack of friendship with the First Nations who call them home. The history is something we are all affected by, as we are all treaty people in Canada. We all have a shared history to reflect on, and each of us is affected by this history in different ways. Our past defines our present, but if we move forward as friends and allies, then it does not have to define our future. Because everyone is tuning in from remote areas across the world, I'd like to encourage everyone to take a moment to acknowledge the land they're on. As a university community, we are dedicated to continue to increase our awareness, understanding, and gratitude for the lands we share. Now, let me welcome Stephen Murphy, President and Vice Chancellor of Ontario Tech University, to deliver his opening remarks.
Thanks very much, Les. And let me welcome all of the panelists and participants to today's online workshop on nuclear renewable energy systems. And let me give a special thank you to our partnership with the International Atomic Energy Agency. I think these were the exact sorts of workshops that we had in mind as that partnership was created and is now flourishing. When I look at some of the objectives of today, it speaks directly to Ontario's tech strengths. Those are advancing nuclear power technology, including small modular reactors, strengthening the synergies between nuclear and renewable. Obviously, this is an are that the whole world is looking to do, to create integrated energy systems that are green, to leverage these systems for multi-purpose applications to serve sustainability and meet the goals of climate change in Canada and many other nations. Many of you, of course, will know that Ontario Tech's strengths are hugely in the energy domain. We have experts in all forms of nuclear energy, from SMRs to reactors to isotopes. As well, we have many experts working in battery technologies, in hydrogen, fuel cells, in smart grids and microgrids, right across the energy spectrum. In fact, I would be leaving people out. And we've created the Brilliant Energy Institute that would be able to house all of these researchers under one umbrella to get at the central question that is really behind what today's meeting is all about. And that's, if we were to actually ask ourselves, what does net zero really entail? So if you go behind the words or the rhetoric that we can hear often used by politicians, what are the actual actions, both upstream and downstream, that would have to be put into place for us to achieve net zero? And that, of course, includes so many aspects of not only consumer choice, but in terms of government policy choices around the grids that we have worldwide. Nuclear covers off the vast majority of the base load here in Ontario, Canada. So it's certainly a well understood technology here. It's really interesting to see the role that other green technologies are playing in the integration of nuclear with other technologies as Ontario's system evolves. It would be nice to see that evolve strategically and scientifically rather than simply as an artifact of what has always been in the past. So I think that this workshop is very much on target for what the world needs to be talking about. I think that energy security tops the world's demands in terms of, as we look to the future, right up there as the same flip side of the coin to climate change, and that the work that we're doing is incredibly important. So let me thank again the panelists and participants today and tomorrow for joining the workshop, and to our friends and allies with the International Atomic Energy Agency. Thank you very much.
Thank you, Stephen. Ontario Tech University was designated as the International Atomic Energy Agency Collaborating Centre in April last year. We're the first IAEA Collaborating Centre in Canada. In this capacity, we support the IAEA activities to advance nuclear power technology, including small modular reactors, strengthen the synergies between nuclear and renewable sources in integrated energy systems, and to leverage these energy systems for multiple purpose applications to serve sustainability and meet the goals of the climate change action of Canada and other nations. Integrated energy systems involving nuclear and renewable sources are among the pathways to face the increasing demand of energy worldwide. Nuclear power can play a stabilizing role in a synergetic operation with renewables. Small modular reactors for base load or load following operation bring an added value to integrated nuclear renewable energy systems in serving off-grid communities and remote areas. In particular, in Canada, there's incredible interest in what it implies also for our resource sector. It is anticipated that integrated systems will reduce investments in transmission and distribution infrastructure. The use of integrated energy systems for sustainable production of electric power and heat can provide cooling, fresh water, green fuels, and other useful commodities associated with a large cut of carbon emissions. This includes the production of hydrogen to supply the growing demand for clean fuels and the need for an efficient medium for energy storage. Obviously, at Ontario Tech, as a world leader in hydrogen research, we take a particular interest in this last point. Over the next 2 days, we bring energy experts from academia, industry, and international organizations to present and discuss the future of synergizing nuclear and renewable energy sources to shed additional light on this timely and important topic in light of the growing interest in integrated nuclear renewable energy systems and their role in the hydrogen economy. It's my pleasure to see over 650 registrants today. This clearly reflects the great interest in today's topic. I'd be amiss to not acknowledge the incredible work by Professor Ibrahim Dincer, who is one of our first Brilliant Energy Institute research chairs, for his incredible capacity at mobilizing and organizing energy researchers from around the world. His skill at this is certainly unique in Canada and quite likely among the very best in the world. I'd also like to thank the members of my team behind this screen who made all these efforts to pull this together, in particularly our IAEA Collaborating Centre Coordinator, Remy El-Iman, and our Executive Director of the Brilliant Energy Institute, Jackie Hornwick. As Hossam already mentioned, it's on one hand regrettable that all of you are not on the Ontario Tech campus for this event, but we strongly encourage you to come when you have an opportunity. Now, I'd like to invite Ms. Aline de Cloizeaux to deliver the opening remarks of the event. She has been recently appointed as Director of the Division of Nuclear Power in the Department of Nuclear Energy of the IAEA. She has extensive experience as Program Director of several new build nuclear projects. She has also engaged in gender balance and diversity actions, notably served as President of Women in Nuclear in France and is an active member of Women in Nuclear Global. Mr. de Cloizeaux holds a master's degree in Science and Engineering Technology from the École Polytechnique, a master's degree in Civil Engineering Technology from the École Nationale des Ponts de Cholet, and an MBA from the Collège des Ingénieurs. I'd also like to take this chance to congratulate her on joining the IAEA. Please, Aline, the floor is yours.
Thank you very much. So, dear President Murphy, dear Vice President Jacobs, dear colleagues and dear participants, thank you, Les, first for your kind introduction about me. So I am happy to be here and to meet you all virtually. We are glad that the pandemic has shown substantial improvement globally, yet proper health measures are still enforced even in Austria. And so maybe sometime we will be able to meet in Canada. So I am delighted to see that we are now implementing the third event of the 4-year work plan for Ontario Tech University as an IAEA Collaborating Centre, which is the first one in Canada. So obviously this has benefited IAEA member states and further strengthened cooperation between Canada and IAEA. Through the Collaborating Centre network, the IAEA can assist better the member state with their original research, development and training in nuclear technology, including their safe and secure application. So the work plan with Ontario Tech University is on topics that are close to my heart. Advanced nuclear power reactors with their non-electrical applications for integrated energy systems. I spent indeed almost 3 decades of my career in nuclear power industry for sustainable energy system, and I've never been stopped being fascinating for this technology. The IAEA acknowledges Canada's important global role in R&D and deployment of advanced nuclear power reactor, including the coming new builds in Ontario using SMRs and microreactors in the integrated energy system. I think that Canada is showing the way to the world, and your experience will be very useful to all the member states. So these topics are also timely as we face the challenge of producing enough energy to power global development and to face climate change issues. And now we have also the security of supply of energy, which is in front of us. So nuclear energy can be used in a more sustainable and versatile way beyond solely electricity production, such as producing potable water through desalination, district heating, providing heat for industrial processes, and generate hydrogen for clean energy, thus bringing great potential to tackle climate change. And innovation, of course, is key to that success. So I am proud that in this workshop, we have the good lineup of distinguished experts from Canada, from the United States, and in-house experts from the IAEA Department of Nuclear Energy, who will chair, moderate, and perform as panelists. So ladies and gentlemen, as mentioned in the prior events, in response to increasing demands from our member states, the IAEA has put in place an agency-wide platform on SMR modular reactor and their applications. Member states, including Canada, are cordially invited to request support from the platform as far as development, deployment, and oversight of SMRs and their applications. We have recently come up with a comprehensive medium-term strategy from 2022 to 2027 to serve member states on the subject. Last but not least, I would like to thank both the liaison officers of the Collaborating Centre, so Professor Hossam Kishawy of the Ontario Tech and University, and Dr. Adid Shubki from the IAEA Division of Nuclear Power for putting together this important event. And I also would like to thank all the IAEA team members who will participate as panelists or moderator in this today's event. So ladies and gentlemen, together with President Murphy, it is my pleasure to jointly open this online workshop, and I'm looking forward to our work together. Thank you very much.
Thank you, Aline. And once again, it's our pleasure to have you with us today. And I trust that this will be one of many times that we collaborate and welcome you. I am now pleased to turn things over to Ms. Tatjana Jevremovic, the project manager and lead of water-cooled reactors technology development at the IAEA and the chair of today's session. She has been a wonderful partner and collaborator for our IAEA Collaborating Centre. So now, Tatjana, the floor is yours.
Thank you, Les, very much. Hello to everyone. Good day around the planet. It is my great pleasure to be here and chair today's two sessions. And many thanks to Collaborating Centre and Ontario Tech to organize such a big event, bringing also experts from the world in the field that will share with us the latest findings and knowledge relevant to the topic of this event. Before starting with the agenda and introducing the participants, speakers, sorry, there are a few very important housekeeping items, especially for our large number of attendees. So first of all, this is an interactive session. What it means that we would encourage you to ask the questions. So that we can have our speakers and panelists later on provide the answers and bring more lights into the topic of interest for all of us. However, we ask you to put the questions into Q&A panel only. If you put the question into the chat panel, that will not be taken by our management team. The chat panel is only used if you do have technical issues, then we will address immediately. Our team will be behind to help you. So for information, all participants, all attendees are muted throughout the time of the event. So the questions to the speakers could be placed again into the Q&A panel, and the questions will be addressed at the beginning of the panel session, not during this first session of the presentations. We have invited the world speakers, experts, and we will be having them sharing with you latest findings and knowledge on nuclear renewable integrated energy systems in supporting net zero goals and sustainable production of energy and heat. And also we will share with you some of the agency activities of relevance to these topics. So I would kindly ask speakers to try to stay within the allotted time. However, we were informed just shortly before the event started that one of our speakers was called by another duty. So Mr. Brett Rampal will not be presenting today. I would like to now introduce our first speaker, Dr. Shannon Bragg-Sitton. Shannon is an internationally recognized pioneer in the innovative application of nuclear energy alongside other clean energy generators, seeking to maximize energy utilization, generator profitability, and grid reliability and resilience through system integration. Shannon is the director for the Integrated Energy and Storage Systems Division in the Energy and Environment Science and Technology Directorate at Idaho National Lab in the United States. That includes power and energy systems, energy storage and electric transportation, and hydrogen and electrochemistry departments. Shannon also serves as the National Technical Director for the DOE, Department of Energy Office of Nuclear Energy Integrated Systems Program, and she's also the chair of the Generation 4 International Forum, Interim Task Force on Non-Electric Applications of Nuclear Heat. Please join us, Shannon.
Thank you for that introduction, Tatjana. And it's a pleasure to be here speaking with you all today. As the first technical speaker within this workshop, I wanted to frame the problem a little bit on first the role of nuclear technologies in achieving the extremely aggressive goals that have been set out for net zero, and ways in which we could perhaps accelerate that deployment through partnerships, through modeling and simulation, and through demonstration activities as well. Let's see, there we go. Let's start by first framing this by talking about what does our grid look like today? How are we meeting our grid demands with our energy resources right now? In most cases, what we see is individual generators that are contributing to meeting the grid demand over a range of time and using a number of different energy markets. And these are managed by independent grid operators. When we look to thermal energy demands, those are typically met by individual resources supporting those industrial demands. And of course, we know that transportation still mostly relies on fossil fuels, with growing electrification, as well as some other areas to reduce emissions from transportation. But many of our countries, nation states, municipalities, and companies have set up extremely aggressive goals for achieving net zero emissions. In the United States, those goals are to achieve net zero emissions in the electricity sector by 2035, and then within the economy-wide net zero by 2050. If we're going to achieve those aggressive goals, and frankly, what is a relatively short timeline, we can't continue with this compartmentalized approach to meeting our energy demands. And we need to look more deeply at all of our clean energy options and how they work together. And we absolutely must begin looking at non-emitting sources of heat in addition to that electricity. And we should do this all at once in a holistic framework. If we look at how our electric grid has traditionally been operating, we have a stack of resources where some are traditionally treated as baseload resources, such as this 2007 view of a one-day period in the Texas region in the United States. What you can see here is nuclear energy is typically operating as a baseload resource, coal mostly as a baseload resource, and then natural gas meeting the dynamics of the variation in the demand. And we have some small amounts of wind and hydro. And this was, again, back in 2007. But as we have more and more renewable resources being added to the grid, what we see is a significant shift and transition in how our grid must operate to ensure that we have reliable and resilient electricity supply. What we see here is a picture of that same type of period, a one-day period, but in 2020, for the California region, where there is significant build out of variable renewables that are used to meet that load. In this particular snapshot, nuclear is still operating as baseload, but as we see more and more of these variable renewables, you see so much more of the dynamic that we now need to meet with all of our generation sources. And what this means is that even those traditionally baseload technologies will need to operate more flexibly in order to meet that variability in the net demand. So we need to make sure that our resources can match that flexibility that is being demanded of them, and that we think beyond this electricity sector and think about how we can do that by sending some of that clean energy to other applications as well. And that's really what we're talking about here within integrated energy systems. So let's look at the magnitude of that problem. So this plot is summarized from many different charts that are put out by the Lawrence Livermore National Laboratory to look at a holistic view of our energy sources and consumers. Now, this is for the United States in 2018. when we begin looking at how our energy is utilized as heat, electricity, what heat we reject in those processes, we can begin to understand all of those energy flows. On the left, you see the various energy sources that are being used in the US, where nuclear energy is only supplying 8% of our overall energy needs today, or 2018. If we were to look only at electricity, that number goes up to about 20% of our electricity supply being provided by nuclear, and 50% of our clean energy or clean electricity being supplied by nuclear energy. What we really need to look at is that big bar on the bottom. When we look at overall energy utilization, 80% of that is still being met by fossil resources. So that is a huge problem that we need to overcome. We need to look at all of these energy flows and understand how those top few resources that are non-emitting can be used to replace that really large bar at the bottom. And when we begin to crunch all the numbers on these energy flows and how it is utilized as electricity, how it is used in residential sectors and industry and transportation, what we find is that electricity is only a small part of the problem. It's only 17% of the energy use in this example from the US. And in fact, when we look at how that energy is used, over 80% of it is used in the form of heat. And of course, nuclear energy is a primary producer of heat. We actually convert that to electricity. So let's look at that as a primary resource and utilize that differently. And that's what we're looking at when we consider these future clean energy systems. So these integrated energy system looks at ways in which we can transform that energy paradigm. How can we look at utilization of non-emitting nuclear energy at a variety of scales, working alongside those other energy resources, such as variable renewables? Municipal waste is another energy source we don't think much about, but can be a significant contributor in the future. We also look at fossil with carbon capture. And instead of just looking at meeting the electricity sector, by looking at this holistically, at directly integrating these resources or enhancing the coordination of those resources within a grid infrastructure, we can look at ways in which we can collectively meet the electricity demand on the grid, and as well as electricity demands in these processes that are shown at the bottom of the chart, and the heat demands of those processes as well. When we look at integrated systems, we want to understand the role of large-scale light water reactors, the role of high-temperature advanced reactors, small modular reactors, microreactors. They all play a role in meeting different energy demands and can do so without emissions. We also need to understand the role of energy storage, shown at the center of this chart, whether that be electrical energy storage that we often think about, but also thermal energy storage or even chemical energy storage, as providing a means in which we can condition the heat from these nuclear energy resources, that we can provide that heat and electricity at the time it is needed to drive the different processes in industry, to meet electricity demand, or to produce hydrogen that can support a number of downstream applications while removing the emissions associated with traditional processes. So if we look a little bit deeper at this, we find an array of options. We find a huge problem in front of us as to how we can begin tackling this integration of upstream resources to meet a wide array of downstream demands. So first, I want you to notice that if we look on the right-hand side, there are a variety of areas in which our nuclear and renewable technologies can work collectively to meet energy demands. If you take a look at the arrows here, you'll see that many of these have various feedstocks that can be supported in different ways by these upstream energy generation processes, whether that be high temperature process heat, augmented heat, meaning utilization of lower temperature nuclear technologies and augmenting that to achieve higher temperature process needs on that right-hand side here, where we can use chemical heat pumps, mechanical heat pumps, or even electric heating to get to those temperatures such that we have an option to use perhaps a light water reactor to support high temperature processes on the right. Some of these also use electricity directly and could be integrated within an energy park behind the grid interconnection. And some require process intermediates such as hydrogen this blue arrow that you see going into many of these processes on the right. So when we think about these integration options, we can think about how they can be integrated using heat, using electricity, or these process intermediates. So there's many options that we can evaluate. We also need to prioritize. So how do we do that? Well, we can begin by looking at that right-hand column and understanding what the magnitude of energy demand is for those sectors within a region or globally, to understand where are the big demands, where are the heavy hitters that we can focus on first. If we then cross that with the emissions associated with these areas, we can begin to understand where we can make significant impact on reducing emissions as well by looking at these integrated options. Let me say a few things about hydrogen as well. Hydrogen can itself be an output and a product that can go out to many different markets, or it may be that intermediate that allows us to produce synthetic liquid fuels that combine captured CO2 with that hydrogen to produce liquid drop-in fuels for the aviation sector and other sectors that are very hard to decarbonize, or that might go into ammonia or ammonia-based fertilizers. And that ammonia can be an easier energy carrier to transport to other applications. So there is a wide array of options, and the highest priorities may be different in each of our regions. But let me just give you some examples as to how we have begun to tackle some of those problems. As I mentioned, our traditional electricity sector looks at single input, single output types of systems. And the models used to predict generation needs and to help our utilities understand what to build in the future don't often look at these cross-sectoral solutions. So capacity expansion models and production cost models tend to look at these individual generators being added to the grid. What we found is that we needed to develop tools to help us better assess the role and the opportunities for these integrated energy systems. So this slide just gives a very quick snapshot of a tool suite that we have developed at the national laboratories in the US called the Framework for Optimization of Resources and Economics, or FORCE. That is comprised of many different sub-tools that allow us to look at how we can optimize the portfolio, what the sizing of each of those individual generators should be to meet specific demands in a region. Once we build that, how would we actually dispatch energy to meet thermal energy demands, to meet electricity energy demands? We bring in very detailed dynamic process models in our hybrid suite of models shown on the right here. And that allows us to understand the system dynamics as we vary those energy flows. How does that impact all of the individual components? We wrap that with a supervisory control system, taking into account all these different externalities that come in when we have different energy demands being met by many different energy sources in the system. And we then wrap that also with that economic analysis such that we can optimize the performance of these systems. Now, I won't go into how these tools work. I will note that they are available open source, and my team is actually running a training session on them last week and this week. And once that is complete, those training tools will be available on our website here if you'd like to learn how to use those and become a part of our user group. So let me just give you a very quick example as to how those tools can be utilized and how they have been quite disruptive. Some of the first analyses that we've used them for is to look at nuclear energy being used to produce hydrogen. My colleague, Dr. Richard Boardman, will be speaking to this topic area in much greater depth tomorrow. So let me just give you a snapshot. This is a partnership, a collaboration across national laboratories and industry to look at the potential of using existing fleet reactors to make hydrogen using high temperature electrolysis while still supporting the electricity grid. And the motivation here was to enhance the economics of existing fleet plants that are currently seeing financial challenges. So by applying these tools to conduct this technical and economic analysis, we can look at the potential economics of performing business as usual and just providing electricity to the grid. So this upper portion of the plot or the figure on the right. But we also then look at the motivations for producing hydrogen, where some of that electricity and heat is diverted to the high temperature electrolysis system in order to meet the demand of the hydrogen market. Now, a key assumption within this study was that hydrogen markets must also be met at all times, just like the electricity market. So we incorporate hydrogen storage to ensure that we can do so. So these tools allow us to look at how we would dispatch that energy. So if I draw your attention to the plot on the upper right, the black line shows variability in the grid electricity price. So when grid prices are low, the system chooses to produce hydrogen and send that hydrogen into storage. But when grid prices are high, it shifts and directs that energy to meet that grid demand, and hydrogen markets are then met by dispatching from storage. And we can also then look at where is this price competitive? What's the price of hydrogen produced using this type of system? And how does that compare to the traditional steam methane reforming with carbon capture and sequestration or without carbon capture? And we can begin to understand those price points. Just drawing your attention to one example here, if we have electricity price of $30 coupled to high temperature electrolysis, we can expect to make hydrogen at about $1.80 per kilogram hydrogen, which we begin to see is price competitive with these competing technologies depending on the price of natural gas. Our overall goal is to actually get this down to $1 per kilogram. So bottom line, this analysis and these types of approaches can help us to understand when it is more profitable to produce hydrogen versus selling electricity to the grid and dispatching that hydrogen from storage to meet those hydrogen demands. This was applied for a specific plant in the Exelon fleet that is now Constellation. And we saw that over a 17-year period, this type of operation could provide $1.2 billion in profit to revenue increase to that plant. And this was sufficient for Exelon, now Constellation, to move forward with demonstration of this technology at the 9 Mile Point plant in New York. And they're installing hardware now and will produce hydrogen beginning later this year. And that is just one of 4 demonstration projects such as this in the United States, again, that my colleague will speak to in more depth. We're now looking at some of these other high priority cases and how we can utilize advanced reactors as well as these light water reactors to support these non-grid applications. One of those first steps is to better understand the role of thermal energy storage in maximizing how we can provide electricity to meet peak grid demand, but also as an intermediate to provide heat to secondary processes such as hydrogen production, steel manufacturing, or ammonia production. We are evaluating the markets that have the greatest opportunity and how we control these different units to send that energy to storage or to dispatch it from storage and the plant itself. And that study will be completed later this year. Another study that we're diving deeper into is carbon conversion. As we begin to move away from fossil resources for electricity production, we are looking at the role of those resources as feedstock to produce higher value products that can be sold into the market. So that coal can utilize heat. We can utilize heat and electricity to convert that coal through pyrolysis and all these steps that are shown here to produce things like asphalt, plastics, polymers, things that we use each and every day, and thereby maintain some of those communities that rely on those fossil resources. So again, this study is underway and we will have results of this later this year as well. And finally, we are taking that hydrogen production analysis to the next step in how we use that hydrogen, where in this case, we're looking at utilizing both light water reactors as well as high temperature advanced reactors combined with captured carbon dioxide from a feedstock plant, or in the future, perhaps captured carbon dioxide from air, running that through different processes. Here we look at the Fischer-Tropsch process to produce syncrude and then refining that into fuels that we use today, diesel, naphtha, jet fuels. We're looking very much at the details of how we couple these different processes, how we dispatch that energy, and then optimizing the performance so that we can provide reduced emission fuels to meet the demands in these harder to abate sectors. So again, this is underway and we're working with multiple national laboratories to conduct this analysis for different regions in which it might be located. So let me just take the last minute or so that I have here to give you a snapshot of what we're doing experimentally We have some experimental facilities that help to support validation of all of these models that I've mentioned, to demonstrate these technologies, characterize performance, and to demonstrate control systems. So this is an overhead view of our dynamic energy transport and integration laboratory that allows us to electrically demonstrate a microreactor, for example, delivery of heat from that to thermal energy storage shown here, and then distribute that heat to other users such as high temperature electrolysis, which is also co-located in our laboratory. We can manage that and understand how that interacts with microgrids using the hardware shown on the right, understand how that works with other power systems in the grid, whether that be a microgrid or a larger grid infrastructure. And then we can use that hardware to also connect to other laboratories to further extend the integrated systems that we can demonstrate within our facility. These facilities are also connected to our human system simulation laboratory that allows us to understand operator interaction with these systems. So we've recently run through a demonstration of what that was like for an operator to run power production for the grid, or to send that energy to hydrogen production. And again, my colleague will give you some of the results of that particular study and demonstration. Quickly, we are also working with the National Reactor Innovation Center, which is refurbishing facilities for demonstration of fueled microreactors to allow us to characterize and better understand the performance of these advanced reactor systems. And we are working with them to ensure that these facilities, such as this dome facility here, will allow us to take that heat from that microreactor to demonstrate how that would be used to support variable thermal loads to represent an integrated energy system. And we expect that test bed to be available in 2024. Similarly, we are working with the microreactor program that is building a microreactor here at the Idaho National Laboratory. This will be a very small scale system that allows us to demonstrate a nuclear microgrid operation. This can support up to 40 kilowatts of electricity production. That's quite small, but it does allow us to connect other heat users as well as electricity users, so we can begin to understand the operation of both a thermal and an electrical microgrid with this system. And finally, this isn't just something we're looking at 10, 20 years in the future, but this is very near term, where that Marvel microreactor will be demonstrated at the end of next year. That will be followed by demonstrations of microreactors in the NRIC facilities in 2024 and 2025, and then working with advanced reactor demonstrators later in the decade, which will first demonstrate electricity production, but also are looking to these heat applications for their advanced reactors. So there's a lot coming. There's a lot of opportunity, and I look forward to hearing the other speakers about what's going on in other organizations and countries around the world. So thank you very much. I hope you will enjoy the rest of this workshop.
Thank you very much, Shannon, for a great presentation. As always, highly insightful, and I'm sure there will be a lot of questions. So we will see either at the end of the session, if time permits, or at the beginning of the next one, we will address them. Let me now introduce our next speaker. Our next speaker is Dr. Ibrahim Dincer. Ibrahim Dincer is a professor of mechanical engineering at Ontario Tech University. He is a leading figure in the area of hydrogen energy technologies, and during the past 7 years, he has been recognized by Thomson Reuters as one of the most influential scientific minds in engineering and one of the most highly cited researchers. Ibrahim is an active member of various international scientific organizations and societies, serves as editor-in-chief, associate editor, regional editor, and editorial board member on various prestigious international journals. He is a recipient of several research, teaching, and service awards, including the Premier's Research Excellence Award in Ontario, Canada. Ibrahim, the floor is yours, please.
Thank you. Good afternoon, everyone. Good morning, of course. The title of my presentation today will be about the integrated nuclear and renewable energy systems for sustainable communities. And I like to briefly emphasize what we do in CERN as part of this unique research lab And we are focusing on hydrogen and fuel cell technologies, renewable energy technologies, energy storage technologies, hybrid and integrated nuclear energy systems, electric and hybrid electric vehicles, alternative fuels, and production technologies. Really, basically, to be able to cover a wide range of energy sources and applications with the cutting edge technologies. And we are going into the subject, but what is critical in here to really look at what people need. People need clean air, clean food, clean water, clean energy. This clean energy is becoming very critical, and if you don't have it clean enough, all of the above listed critical items will be affected drastically. So really, the prerequisite is going to be really clean energy. Let's look at the clean energy portfolio. And I always try to illustrate things in a simple manner. And where we start, really basic essential tools coming down from thermodynamics, and really having exergization as a tool coming from the second law of thermodynamics for design, analysis, assessment, and performance improvement. We need to work on greenization, really to be able to greenize our existing systems to make them more environmentally benign. The next is going to be really about nuclearization. So it is becoming very critical now to bring innovative nuclear solutions into and really diversify this portfolio and provide cleaner solutions. Renewabilization is going to be another topic, of course. We need to be able to really deploy renewable energy technologies and utilize the existing renewable energy sources. Of course, the next is going to be really about hydrogenization. And we need to really produce hydrogen and serve for a hydrogen economy. System integration is becoming very critical. And then storagization accordingly to be able to incorporate into the systems and really offset the mismatch between demand and supply, becoming very critical. And then the next is going to be really about intelligization. And we really need to look into AI tools and implement into the energy solutions. So when we look at this diversified clean energy portfolio, we need all of this. So now I have this illustration. This illustration is very basic. And I have my 3S concept. And this actually 3S is going to be needed for double S. So which is sustainable society. So if we go back, accordingly see what is available. And basically we have three options: fossil fuels, nuclear, and renewables. So if we put the fossil fuels aside, what is left? Nuclear and renewables. So now we need to look at the systems, and systems to be able to produce what is needed by this society. And we can look at this as really to produce from hydrogen to heat, electricity, cooling, fresh water, even other, let's say, fuels and other useful commodities. And then now, the other important part in this, to look at also hydrogen production methods. And if you look at these fossil fuels, essentially what we currently use, which makes it about 95% really for hydrogen production, and producing hydrogen from these will not make sense. So what will make sense here, you see, this is very important. What we see in here, basically nuclear and renewable energy options. So basically to be able to produce clean hydrogen. And how? To, by dissociating water into hydrogen and oxygen. And then I have this nuclear renewable farm concept. This is very important. And what we do, and the farm concept is utilized in various energy applications. But now when we come down to nuclear and renewable options, so what will happen? We need these sources, as you see, source nuclear all the way down to biomass, covering the entire spectrum of renewables. And then what is needed at the end, if we target to produce, let's say, specifically hydrogen, and what is needed here, we can really dwell on technologies ranging from thermochemical and hybrid cycles to high temperature, low temperature, even photonic methods to be able to produce clean hydrogen. And then a quick overview here, and we had a couple of kind of update on hydrogen-related research and development activities in Canada, and really to look at it countrywide and see really who is leading, who is empowered. And when you look at the really scholarly publications, really patented technologies and others, and what we see in here clearly, Ontario Tech is leading. So our institution is really leading in Canada. And also to look at the hydrogen production, because that is becoming really the key requirement in hydrogen economy. So if we are going to really look at this, and we need to address multiple things. And I introduced them by this 18S concept, really to look at entire spectrum, and from technical to social, even going down to economic or other standards or costs related, and then making this entire spectrum to be covered. And this was right after my keynote talk in 2017, and then materialized it into this study to really cover them, discuss them, and provide a unique guidance to the readers or researchers. And also based on this 18S concept, and they studied the entire to look at various technologies, thermochemical, photonic, CERL, ideal case, to see ideal is going to be 1, and try to rank them between 0 and 1, and really mapping out through this kind of web diagram, and then developing these, and then studying them accordingly. These are becoming very critical, and we need to implement these, especially for the integrated system. To look at what else we have got in here, basically thermochemical hydrogen production research started with basic cycles, getting into copper chlorine cycle. This has been a kind of institution-wide project covering multiple research groups in and out. And then, of course, next, in my research group, really studied the magnesium chlorine cycle and then other potential cycles, and getting into integrated systems. So the way we have been doing it, an ultimate goal is really becoming to develop integrated systems for sustainable communities. And then, of course, we did the lab scale integrated copper chlorine cycle. And this was, again, a large work, really developing and building, and in the lab at the CERN, and with multiple researchers. And then getting into magnesium chlorine cycle. And really, this cycle wasn't new. It was, of course, developed ideally by a chemist, but what we did, we engineered this cycle. We engineered it in a way to be able to develop integrated systems out of it. And then next, to improve the actual cycle by considering these three steps. And there were three steps, and we improved it and really developed four-step cycle. And then also sodium hydroxide. This is also another important cycle to implement, especially with solar and nuclear, or even in an integrated fashion, to look at the options, because the temperature will go up to 400 degrees Celsius, suitable for the, let's say, present, let's say, reactors, nuclear reactors, or MPPs, and then also additionally for the generation for reactors. And we do have a heat upgrade option if the heat level or the temperature level is not sufficient to achieve the cycle. So we'll be able to upgrade the heat and bring it up to the desired level, and then really functionalize the process. And then I consider a few key points to make in here, and this is very important. And when we look at the systems, we have to keep in mind it is becoming very important, really, for multi-generation. And what options we have got? Really to combine the system, to hybridize the system, to integrate the systems. And also keeping in mind modularization is going to be necessary. So when you look at this, really integration for multi-generation, and what we see in various sectors, and this is something interesting, I included this from the food sector. And look, 2-in-1, and then, for example, 6-in-1, 10-in-1, and many more, showing that, you know, multiple ingredients will be added into to make one integrated product. So why not really applying a similar approach into the energy technologies or systems in general, and then develop this? And the concept is here. You see the basics behind when we consider thermodynamics with the same input to be able to produce multiple useful outputs. This is the target. And also started developing integrated systems to look at of course, various types of reactors, and also incorporating various types of hydrogen production technologies, and making the systems really as desired by the community to be able to provide useful outputs, and also doing the simulations accordingly in the Aspen Plus. And I mentioned that we have developed heat upgrading options. Heat upgrading is going to be very important. And I have had multiple graduate students jointly supervised by one of my colleagues, and really trying to develop cascaded heat pump options. And these heat pump options are really important to develop, and really make them suitable for the nuclear power plants to be able to really use for thermochemical and hybrid cycles. And also at the same time started looking at, you know, for different communities. This is a unique study for Canada. Consider the Nunavut territory with indigenous communities around, and trying to look at the system in an integrated fashion, where we have a small modular reactor, and at the same time to be able to utilize renewables, and really to be able to cover multiple useful outputs, from energy to food, fuel, etc. And really also deploying copper chlorine cycle into, and at the end, really achieving the goals even for the United Nations sustainability goals to be able to address 6 of them. And then getting into further, and this was for the Saigon First Nation community, and developing something similar by considering the nuclear power plant there, and then really incorporate this scenario and with solar energy to be able to cover again what the community needs. And really basically from electricity down to food and also other clean water, etc. So to be able to provide this. Similarly, another one, this was a very interesting study, and by considering the current Diopol Canyon power plant, taking it, integrating under a scenario with solar power and incorporating the systems accordingly to be able to address the needs. And then in Oshawa, and I am going to be finishing in a couple of minutes, and this is a unique study. And I led a project, and the project was about Oshawa hydrogen hub development. And in this case, what we did, we looked at the really Durham region, but in a specific Oshawa, and considered the sources. The sources were nuclear. We have got nuclear power plants around, and then solar, biomass, wind, and hydro accordingly. And then also identified potential methods as we have been developing at the university, and then really targeting to develop and produce hydrogen, clean hydrogen, and also along with some other useful commodities, as mentioned earlier, and then really supplying to various sectors. And also published some of our results in last year, and the scenario, of course, under a different consideration to look at the entire Durham region as well, and then trying to cover basically essentially transportation sector in general. And then we clearly see here what option is becoming very critical: nuclear hydrogen and renewable hydrogen. So again, various scenarios to consider in terms of production and also transportation. Even different types of vehicles are considered under different scenarios with refueling stations. And also did a couple of life cycle assessment. You know, my group has done those. And to look at the actual options available, and in terms of cost, emissions, etc., we have just updated this based on the current increased diesel prices. So when you see here, and this is becoming really not feasible, even economically. And of course, from the environmental impact point of view, is becoming really nonsense. Look at the CNG option, and then of course, battery electric, and then fuel cell electric. So these are becoming very important options. So really by considering them. Additionally, to look at the actually ammonia production. Ammonia production is mentioned by the previous speaker, and we have been studying these options as well. And again, consider different scenarios from nuclear to renewables, and then producing hydrogen. And then what we do here, we really separate nitrogen from air, and then synthesize with hydrogen into ammonia. When we have ammonia, we can use it as fuel, refrigerant, working fluid, even agent for various, let's say, commercial products, and also, of course, supplying to various sectors from agriculture to industrial. So these are becoming very important. And then finally, I like to close by saying that hydrogen age is very critical in here. So diversified sources are needed for a sustainable hydrogen economy. So development of hydrogen sector should be the first priority. And really what is becoming very critical in this, really to be able to hybridize nuclear and renewable energy systems and to serve to really provide sustainable communities. That's all actually, and thank you.
Thank you very much, Ibrahim, for a fantastic presentation. Let me now introduce our next speaker. That's Brianna Lazerwitz. Brianna is an economics, energy, and the environment, as we say, 3E, analyst within the International Atomic Energy Agency, Department of Nuclear Energy. Previously, Brianna worked as a US power policy and finance analyst for Bloomberg NEF and as an energy economist for the US Federal Energy Regulatory Commission. Brianna holds a master's degree in economics and international relations from the Johns Hopkins University School of Advanced International Studies and a bachelor degree in policy analysis from the Indiana University School of Public and Environmental Affairs. Over to you, Brianna.
Thank you, Tatjana, and hi, everyone. My name is Brianna Lazerwitz, and today I'm going to speak to you about how electricity market design impacts the economics of operating nuclear power plants in liberalized power markets with increasing shares of renewable generation. So today I'll speak about, as I mentioned, liberalized power markets, so organized wholesale markets. So I'll be digging in a little bit deeper into each aspect or sub-market. So I'll touch on energy markets, capacity markets, ancillary service markets, and carbon markets. And tying all of this together will be considerations for system costs, emissions, and nuclear economics, and while these markets are evolving due to increased renewable penetration. So in liberalized energy markets, the market clearing price is determined by pairing the volume of energy demanded. Here, if we stack up an example power system with the lowest cost combination of resources that can meet that demand, depending on the energy mix of the particular market and the needs of the end users. Natural gas or coal typically are the marginal unit, the price setting megawatt that determines the price that all resources are paid. This is because of this, what I'm showing here, the merit order design of energy markets, where electricity prices are stacked in order of lowest to highest short run marginal cost, as depicted in the figure here. Nuclear power has a lower marginal cost than natural gas and coal-fired power plants, meaning that additional renewable deployment will just shift this merit order stack further to the right. So showing that if we add additional megawatts of variable renewables, we don't necessarily replace nuclear power, but we're first rather going to be ousting relatively more expensive natural gas and coal from the market. Because nuclear, as our previous speakers have already touched on, can provide that necessary flexibility in order to accommodate the variability of renewable output, nuclear power and renewables can actually be thought of as complements and not substitutes in the energy market. So it's important to understand the evolution of power markets over time. And here we're taking the Ontario power market as an example. These charts show average power prices and net demand in each hour averaged over the year. So each chart shows an average 24-hour daily profile for the year. Net demand is total market demand minus wind and solar output. Net demand basically shows us how much demand can be met by non-intermittent resources in each hour over the year. And these charts show how Ontario's grid has changed as the share of renewable generation has increased over time. In 2016, Ontario's combined solar and wind output was about 1 gigawatt. By 2019, that reached 1.3 gigawatts, a little bit higher. And so far in 2022, renewable output has averaged 2 gigawatts, so almost double from the past, and about 95% of it is wind. So just 5% solar, but we are seeing a big evolution over time for how the market has to react to this integration. So price volatility, you can see the energy price, that blue line, getting a little squigglier over time. The prices have also shifted to match that shape of net demand. And keep in mind the prices look even higher this year due to the increased price of natural gas. Again, that merit order effect that I just spoke about. So as the share of intermittent renewables grows, price volatility tends to increase in the market, and the shape of the energy price curve also shifts. This creates both challenges, but also some opportunities for nuclear. So if we match up the capacity factor, the percentage of the entire year that a resource is operating, and the total cost of those operations, we get a curve similar to this one. Markets have baseload generators, which are operating many hours of the year and thus have a low cost per megawatt hour of generation. We have intermittent and flexible generators, which operate less hours of the year, meaning fixed costs are spread over less megawatt hours of generation. And finally, there are those peaking generators, which operate only a few hours of the year, but are very expensive to run as a result. There may be an instance when providing energy is extremely expensive, whether that's because of very hot or very cold temperatures, because of an unplanned power outage, or some other grid event that causes a lot of generators to become unavailable. Because of price caps that are imposed in energy markets, some years exhibit this missing money problem. That is basically the cost to provide energy in some few hours of the year actually exceeds the energy market price cap. This missing money can be made up either through capacity or scarcity payments, which I will get to in the next couple of slides. Capacity markets and ancillary service markets are a way to supplement the energy prices while also incentivizing certain behaviors from generators. And they become very important for nuclear generators. So this chart shows average capacity and energy market revenues for nuclear power plants in PJM. And you can see where PJM is in the US for those not as familiar, on the top right of the slide. In some years, estimated nuclear unit costs aren't covered by capacity and energy revenues. Since 2008, energy revenues make up about 85% of a nuclear plant's total revenues, while the capacity revenue makes up about 15%. So we can see here the interaction a little bit between the locational marginal price, the LMP, the blue bar here, and the capacity revenue, and kind of a little bit of a top up onto the energy revenues that these plants are earning. So capacity markets, back to this similar chart again, a mechanism to ensure that available electricity supply can meet a peak demand, those few hours in the year where things might get kind of crazy, where demand is very high for whatever reason, and we need to make sure that the power plants, there's enough capacity available to meet that peak demand. So how these work, a little bit different than an energy market, whereas energy markets are run in day ahead increments all the way down to 5 minutes. Capacity markets are run once every several years in order to basically have as a planning mechanism. So participating resources submit their bids that represent the cost of providing energy during peak demand. Because capacity markets supplement the energy markets, basically they're providing a medium-term security of payment for capital-heavy investments such as nuclear power plants. So depending on the capacity market rules and clearing prices, regions with capacity markets can be favorable for new nuclear development, since the capacity market provides a sort of security for capital expenditure recovery. Short-term fluctuations in gas prices, similar to kind of what we're seeing now, those are less likely to impact capacity prices. since coal or oil resources tend to be the marginal clearing technology during peak demand conditions and not gas. So capacity auctions are offered every 3 years in advance for some countries, the US and Australia for one, some countries like the UK, Belgium, France, and Japan, 4 years in advance of the delivery year. So if we imagine a power system with a high share of renewable integration, it might look something like, like this. Where we're shifting the stack out again. Organized wholesale power regions with capacity mechanisms and a high share of renewable generation, which tends to be subsidized, states or provinces incentivizing additional renewable resources. This actually risks reducing the share of low carbon nuclear generators in the market by artificially suppressing the capacity market clearing price. So without capacity market revenues, nuclear power plants are increasingly likely to retire. It will be pretty important to send clear market incentives to keep low carbon baseload and flexible generation online in order to balance that variable renewable generation. There we go. Energy reserves, the third piece here as part of the ancillary service market. Scarcity pricing is a market mechanism that acts as another adder on top of energy prices to send an economic signal of system stress. So this is operating in the energy markets again. So we first discussed energy markets that are running and sending incentives to deliver power in up to 5-minute increments. And then we discussed capacity markets, which is just an additional, you can think of as a lump sum payment in order to keep resources around for when you need them. Now we're going back to energy markets to discuss ancillary services. So what these markets are trying to target is when reserves fall. So when your backup generation is paid based on how quickly it can respond to a disruption in system generation. So real-time scarcity pricing offers the opportunity to compensate resources for super fast flexibility. A scarcity pricing mechanism incentivizes resources to respond and take advantage of price spikes when the supply and demand balance gets a little bit thinner. These price adders are technology neutral and they pay just for flexibility and the resilience necessary to operate a grid, and are increasingly important with higher and higher shares of renewables on the system. The implementation of efficient real-time scarcity pricing like this could translate to better returns for nuclear projects, especially newer generation nuclear, which has the technical ability to ramp up and down over shorter time periods. So what does that look like in real life? Scarcity mechanism reforms, including payment structures, will be vital to maintaining reliable power as variable renewable integration increases. So let's look at what this means in practice. This chart shows daily energy and ancillary service prices in Ontario so far in 2022. But let's zoom in a little bit to a day when market demand peaked and when prices peaked too. So as an example, on January 25th of this year, when demand was highest in the day, you can see how energy and ancillary services interacted. Energy prices are highest, followed by the 10-minute reserves. So these are resources that are online and ready to respond within 10 minutes, followed by 30-minute reserves. This relationship that you can see here on the slide is always the same. Energy prices are highest, followed by shorter term reserves, and then longer term. So the longer it takes a generating resource to respond, the less it's going to get paid. Higher prices indicate the ability of these products to quickly respond to the fluctuation between energy supply and energy demand. And now turning to carbon markets, the Regional Greenhouse Gas Initiative in the US is a cooperative effort among 11 eastern states. You can see again at the top right. which requires coal, gas, and oil-fired power plants in the participating states to pay a fee for their carbon emissions. We call this RGGI. The RGGI-wide CO2 cap represents a regional budget for CO2 emissions. As states join or leave RGGI, the aggregated cap is then reflecting those changes. So the last RGGI auction took place on December 1st, 2021. So you can see the chart is updated to that. The most allowances were traded at a clearing price of about $13 per ton of CO2, the highest since the market began. RGGI's emission cap increased in 2021 as well, but most of that was to accommodate another state that was added. So this US, as an example of a US carbon market, attributes a rising price to carbon, and the plants within these states are likely to earn higher revenues. As a comparison, we've got the EU ETS carbon market in the EU, the world's largest carbon market, and currently the biggest source of demand for international credits, making it the main driver of the international carbon market and main provider of clean energy investment. Some have argued that there are two major disadvantages to this market. Well, because it excludes credits from nuclear energy projects. The first is at the high price of ETS allowances. You can see here the EU ETS price is much higher than the US carbon price in RGGI. Has an effect on electricity prices in Europe, and the power sector emissions from the EU aren't falling as quickly as they need to. So more on that in the next slide. Including nuclear in the EU ETS would increase the number of credits, which could help to lower the carbon price and thus lower electricity prices, and would have the added benefit of allocating a new revenue stream to nuclear power plants while increasing available financing for green investments. So the inclusion of nuclear and keeping operational nuclear power plants online through these additional revenues could help European countries reach climate targets. So using 2029 as a baseline to kind of filter out the pandemic 2020 outlier, power sector emissions would need to decline at an average annual rate of 6% per year in the EU to reach zero emissions by 2035. So just a quick snapshot showing basically that emissions aren't falling fast enough because clean power isn't replacing fossil fuels fast enough. And where it is, it's now replacing gas rather than more emissions intensive coal, which further slows the progress. So I'd like to end on this slide as a reminder for the three key elements of an optimal grid: clean, cheap, reliable. The structure and design of electricity markets has to adapt to changing supply mixes and ensure the security of supply with increasing deployment of variable renewable energies. While regulated markets can ensure nuclear power returns, liberalized markets, so discussed today, have to be accompanied by adequate scarcity pricing mechanisms and potentially capacity markets or other market mechanisms to guarantee suitable flexibility. Accurate market pricing signals directly impact the economics of operating nuclear power plants. To create a low-cost, decarbonized future, decision makers should look closely to price signals and what they incentivize. More flexible, low-carbon generating resources should be adequately compensated. So, thank you for your time and for listening to my presentation.
Thank you, Brianna, very much for a very insightful and a nice presentation. As I have mentioned at the beginning of the session, we are informed just before this event that Mr. Brett Rampal will not be able to join us. He was called for another duty. So the following presentation is by myself. So just very briefly, I come from Europe. I hold PhD in nuclear engineering from the University of Tokyo. I lived in Japan for around 11 years, worked in academia and industry, and also United States at 2 universities. So my career is half in academia, half in industry. and management. So I decided today to present to you basically about the academia side that is very important for our member states to share the knowledge and to provide information of how they can access some of those tools. And at this point, we are focused on presenting on e-learning tools for hybrid energy systems. And these are basically developed within the framework of the IAEA Collaborating Centre established at Pakistan Institute of Engineering and Applied Sciences. My colleague Hasib Urrahman was supposed also to be here and present, but he was also called for another duty. So that's why I take his role at this point. So I will tell you a bit about the Collaborating Centre, because these two centers at PIAS and Ontario Tech, we consider like sister centers, and we overlap in some of the very important topics of interest to a wider community in the world. And therefore, it's important to kind of understand the synergism. And then I will tell you about these education and training tools in general that we have, could be of interest to some of our attendees, and then provide you with the demo video on our e-learning module on hybrid energy systems. So the Collaborating Centre at Pakistan Institute of Engineering and Applied Sciences, or PIAS is called short, was acknowledged on December 5th in 2019. And this is the photo. The delegation was here, so we met in person. As soon as you know, after that, we were faced with a pandemic, and the World Health Organization basically declared the outbreak of COVID-19 starting date on March 11. So the ID card that you can see here of our Collaborating Centre was developed not knowing that pandemic is coming and that might change the way of our business as usual. So the objectives and activities and the work plan that we established for the duration of initial 4 years of the existence of the center was, of course, planned on possibilities to have a wide interactions worldwide, considering that PIAS would host training courses or some other similar events. So we had to very fast turn around and understand how to continue without disruption in realizing our work plan items or tasks. And they are within the 3 pillars of the research development and capacity building for multidisciplinary applications of advanced and innovative nuclear power technologies. So we are focused on modeling and simulations and VNV. VNV stands for verification and validations. Also experimental facilities in a way to utilize the capabilities of the PIAS Center with their labs and connect to VNV activities in regard to modeling and simulations, and education and training, because PIAS is a education and training institution as well, in addition to research. So then we would plan to have events that supports education and training in the region and also other member states of the agency. So this is just a snapshot to tell you that the work plan had a number of objectives across the board of tasks of interest to agency, PIAS, and of course, the benefits to member states. So we were trying to address each of those, and one of very important that overlaps with the activities at the Center in Ontario Tech is in regard to hybrid energy systems. Education and training, and also producing relevant technical and education publications. So in that respect, let me now shed a light on in general, education and learning tools that agency can provide to our member states at no cost. So they are used to support the human resource development and capacity building, specifically in embarking countries on nuclear power program, newcomer countries, but also countries with developed nuclear power programs to sustain the human resource. So our approach is to look into the basic education on a nuclear power plant operation, and therefore provide tools for understanding of the basics of the physics and technology, and also keep abreast of developments in the world and keep informed our member states on new designs and how they evolve in time. So we have so-called educational simulators. There are two types. One we call full nuclear power plant basic principle simulators. That means they reflect on particular technology, but they are not to be used for research, safety analysis, or any of those for any particular type of the design we did and class. We have around 10 different learning basic principle learning simulators, PWRs, PHWRs, BWRs, and so on. And also a few more are coming along. One of which will be on high temperature gas reactors, sodium fast reactors, and severe accidents in PWRs. So they are available online. And if you just Google IAEA principal simulators or just simulators, the page will come, and you will be able to understand how to ask to have the access to these simulators. We also provide training courses. In these 2 years, everything is virtual, and these virtual courses are extremely efficient, the way how we realize to compose them and to run them. So if there is any interest at the national level or regional level, we are more than happy to come and provide such training. Another group of educational simulators, we call them part-task simulators, which means they are addressing a single phenomena or a system or a subsystem of relevance to some of those typical reactor designs. And the agency is now developing so-called HOPES platform that will be collecting this type of simulators for free exchange with member states. So we expect to launch in the second half of this year. For both, the user needs so-called Nucleus account, and this is very easy to understand how to do once you get to those pages. So the Collaborating Centre at PIAS is heavily involved with us in developing a number of these part-task simulators, and a few of those are relevant to hybrid energy systems. So the full nuclear power plant basic principle simulators, we just issued a booklet that will be also available online. And this booklet or brochure basically summarizes all aspects of the simulators, what they can do, what they are, how to apply for, and relevant literature or publications that we also issued as a complementary or supplements to these existing materials on these simulators. Speaking of part-task simulators, these are, as I mentioned, will be available at the HOPES platform by the second half of this year. The second group of tools, learning tools, education and learning tools are what we call e-learning modules, or e-learning classes. So e-learning module is designed to be a limited time learning platform on a specific topic and incorporates a number of interactive features like animations, narrations, video clips, and interactive questions. So we have developed a number of those currently available also for free, with the user needed to have a Nucleus account to access the page. And again, you can just Google e-learning modules IAEA and the page will come. So these e-learning modules or courses or classes are again open to all our member states for free. So that's how the page looks like, and these are structured within the main topics of the agency activities. Our within the nuclear technology, and applications. Then we have nuclear safety security, safeguards and verifications, and cooperation partners. So currently what we have here, you can see those green are available, means published. Actually, the PHWR is also published. So some of those are developed by PIAS, some of those in cooperation with PIAS. Mainly PIAS has took a lead and developed those on hybrid energy systems and natural circulations. And we have some more coming along. One might be of interest on thorium-based reactor concepts, the other one on reactor physics with Python interactive tools that's going to be released probably in a few months and also be available for our member states. This is basically popularity. So as you can see, we start launching those modules by around end of 2020, September 2020. And from then until now, we do have really very good number of participants or users accessing our modules and also providing us with the valuable feedback. That's also kind of gives you an idea of the number of users per country. So we can see those are the top countries, but we have practically over 150 countries that showed interest in these e-learning tools. So here is just a snapshot what they have, what they provide you with. So they provide you with the very basic overviews, build the introductory background information upon which then you move forward with more complex concepts and more details per each of specific designs. We also provide some examples of some of the designs what is very important, all these are summarized in a way to show the historical development toward current, the most evolved or innovative designs. And that's very important to understand how this technology successfully moved in time and continuously is developing and providing the responses as expected. So the e-learning module on natural circulation was developed by PIAS, Collaborating Centre at PIAS. And also this is the first part providing just a very basic introduction to phenomena to provide enough background to understand what is natural circulation and how is that applied in nuclear reactors and what that means when you have natural circulation, what kind of safety features that brings to the design. Hybrid energy systems is an initiative, worldwide, of course, but agency-wide initiative. So you will hear through our panel session today and also presentation tomorrow and tomorrow's panel session as well, and get a good idea of how active agency is in understanding what is the interest among the member states and where the member states go with the concepts of hybridizing, basically making systems that nuclears and renewables would be, so to say, working together. And this module is developed with the idea to provide basic information about what hybrid energy system or integrated energy system is, and also provide the background information why there is such concept. In addition to that, there are a number of examples provided and explain how that works from technology point of view, and also what are the challenges, the gaps, and needed R&D in order to move forward to deployable level. Now, what is new also is that all our e-learning modules are now in the process of being translated into UN languages. As you know, we have 6 UN languages, and this is the one that is already translated in all almost all, but we are now in the process of testing, and the one that is completed, you will hear at the end of the promotional video that I will be asking the host to just show now. Thank you very much for helping with the video. So I hope you now have an idea what agency can provide to support learning. Now, I would suggest that because I was told also that one of our speakers is called to another meeting, so I would like to spend the next 15 minutes addressing some of the questions that came from the audience. So I have a first question for Shannon. So Shannon, what is your view if a country decides to embark on an integrated energy system with the inclusion of nuclear to serve for electricity generation alone? Will it still be economical to embark on such an integrated system if you mentioned that, since you mentioned that electricity contributes just a small portion, like 17% at the United States? Thank you.
So that's an excellent question and brings something very important to the discussion. It's that all of these analyses need to take into account a very region-specific focus, in that what we find might work in California may have absolutely zero application in Florida. And again, translating that globally, it might be quite different. And so it depends on the generation mix in a particular region. It depends on the demands. And it also depends on the energy markets. We have many different market structures within the United States. So that also impacts the economic feasibility. Now, one thing that we do need to understand is that as our electricity mix evolves and we have more variability in it, other resources on the grid, such as nuclear, will also need to be more flexible. So we have to think about ways in which we can do that. So there's two ways that we discussed in that presentation earlier. One is to flexibly provide electricity to the grid by storing it and delivering it when it's needed. So that can be considered a type of hybrid system where we're storing some of that heat, converting to electricity to provide peak power demands. That might be quite profitable in some regions. Currently, we have nuclear plants that are operating flexibly by turning down power. That isn't necessarily an economic operation, because now you've taken that great investment in your nuclear plant and you're only using it part-time. So I would have to understand the scenario a little bit better, but we are also looking at electricity-only solutions, particularly with that thermal energy storage case that I mentioned, because it gives us that flexibility while still utilizing the resource to the maximum extent. I will point out that the tool set that I mentioned that we've developed, that allows us to look at that region-specific data. We bring in region-specific electricity market data. We look at time evolution in electricity demand and prices. We can look at evolution of the other markets in that to drive those analyses such that we can understand economic viability given that very particular location that's being considered.
Thank you, Shannon. I have two more questions for you, if you're good. Okay. So the question is, what is your opinion on the development of standards for the hybrid energy systems? Are there any studies on that subject, given differences of standards among countries?
Those are starting just now. So within the United States, the Electric Power Research Institute is starting up a study to look at kind of a standard set of considerations when you do look at embarking upon integrated energy systems. I think that will be out maybe next year. I'm not sure exactly. When we think about standards, I can hear that in a couple of different ways. I can think about that with regard to how we approach it. Do we need to do things very consistently from plant to plant? And I also think about that from a regulatory perspective and those types of very stringent standards on the approach. From a regulatory perspective, we have also stood up a group in the United States that looks very specifically at the hydrogen applications, beginning to look at regulatory approaches around co-location of hydrogen production facilities at existing fleet nuclear plants, PWRs and BWRs. And then we are also extending that invitation to participate in that group to advanced reactors so that we can begin to look at commonalities, to begin to understand how we need to address potential additional risks associated with co-location initially of hydrogen production, but then also other industrial facilities. We can also begin to look at other impacts and events that could be introduced in this particular scenario. What are the operational considerations? So we're looking at that question because of the variability in how these integrated systems could be developed and what different structures could arise. It's a difficult question to come up with a singular answer on standards that are needed, but I do think that there will become some things put in place as best practices, perhaps, to help us with the regulatory aspects of implementing and deploying these systems. And if anyone would like more information about those groups that I mentioned, that the Hydrogen Regulatory Research Group, and we've also done some preliminary studies on probabilistic risk assessment associated with co-location of these facilities and thermal integration of these facilities, I'd be happy to provide some connections offline.
Thank you, Shannon. And one more question for you. Can you provide some view or your opinion of the challenges from a regulatory point of view for deployment of hybrid energy systems, both in terms of design provisions and operations?
Sure, and that gets at what I was just saying. We're starting to look at that. The work that we have done with current fleet plants, those utilities that we are partnered with have indicated right now that they are under their current license infrastructure for these small-scale nuclear plants and small-scale hydrogen facilities at those nuclear plants. They don't foresee any need for license amendment, and they are proceeding with those facilities. There is a question at what scale would it require any type of license amendment? At what scale of power offtake from those facilities would we require amendments to those licenses? And then we also have to look at the minimum distance between those facilities for transport of thermal energy to produce that industrial product. And we want efficient transport of that energy, but then we also want to ensure that we are safe and have a safe distance between those facilities so that we don't have any interactions between them where some unanticipated, low probability accident in one facility would impact the other. So that is ongoing work right now as far as the regulatory infrastructure with the current fleet plants, and our utility partners and operators of those plants are working with our Nuclear Regulatory Commission. With regard to advanced reactors, we're just beginning to look at that and understand what those challenges may be and how we can approach that. In fact, the Nuclear Regulatory Commission holds a regulatory information conference each year, and just a few weeks ago held a session on this topic specifically about what's coming and how the regulators can begin looking at those challenges so that we can begin interfacing with those that are making those decisions on license impact at the time of design. And so I would say we're starting on those processes. We're starting to consider those questions and check back, and we'll see how those have evolved over time. There may be some translatability between what we do in the US to other countries and vice versa.
Thank you very much, Shannon. I have now a question for Ibrahim. So Ibrahim, the question is, if you would explain or comment how the siting is critical to a nuclear renewable energy system. On that note, must such an integration be considered purposely for off-grid communities, or it is as well important for grid connection? Which energy source should be near to the other in terms of fuel source, considering that renewables such as solar and wind need to have sun and wind? Please.
Thank you. So the question has two dimensions. One is really to look at the grid independent systems, and one is grid dependent. So depending on now, especially we are moving into kind of smart grid applications, and the smart grid applications will be in a way something specific to the community. So that may be really independently for that particular community. And developing a small grid within that community to be able to cover the needs. The key point over here to develop sustainable communities where we have certain specific sources. We may have a renewable, let's say if we are targeting to, let's say, deploy an SMR, or and/or depending on renewable energy systems accordingly, the type will depend again on the sources and what types of systems to develop and integrate with, let's say, with an SMR, and to be able to cover the needs for the targeted sustainable community. And what will make the community really sustainable here, and in terms of energy. So energy is going to be one critical dimension. As I also mentioned, it is linked to air, linked to water, linked to food, and other dimensions as well, especially if you are considering other sectors. So energy is really a key driver. So accordingly, and developing such systems will be very critical, and making it really grid dependent or grid independent, depending on the application. You may localize it, you may make it really plant specific or application specific. So there are various scenarios. And by the way, and I have presented a couple of scenarios. Those were really specific to the certain indigenous communities, and making it that way very specific and targeting to really produce what they need. So that was ultimate goal, including storage options as well.
Thank you very much, Ibrahim. I have one question for Brianna. Brianna, would you please shed a light and explain dynamics of price change resulting from renewable energy sources?
Sure. So I'm also happy to talk offline a little bit more. In the interest of time, I'll kind of try and summarize the impacts on the different markets that I discussed in my presentation. So in energy markets with increased renewable penetration, we see more variability hour to hour and season to season. And so linked to that, in ancillary service markets, we're seeing more reserves being called on more frequently because the renewables introduce more variability into the system. So there might be more hours of the year where reserves, that supply demand balance gets a little bit tighter, and so that the average price of ancillary services will increase over time with more renewable penetration. And capacity markets is a bit of a tricky one. It depends on several factors. If there's lots of renewable penetration, different capacity markets around the world either permit or limit the participation of renewables because it's hard to rely explicitly on renewables for the type of output that a capacity market is trying to incentivize, right? You want to make sure that a resource is available in those peak hours when you really need it of the year. And so that's difficult to do with renewables, right? Unless they're paired with a battery, for instance. But in some capacity market systems, I mentioned PJM in my presentation. It's one region that is starting to struggle with more renewable integration and what that means for the capacity market. In PJM specifically, there was a rule that was passed limiting the amount of participation from subsidized resources, whether that is renewables or nuclear power plants that are getting state subsidies in the US. And so these types of rules are trying to kind of even out the playing field a little bit when it comes to the price signal that the capacity market is sending. But that is very specific to each individual region and the capacity market itself. But by and large, with more renewable integration onto a grid, capacity market prices on average, you'd expect them to fall over time as more renewables are joining the capacity market.
Thank you very much, Brianna. And the last question is for me, basically, The question to summarize is how these e-learning module and part simulators can be used, can students use, can be used for national case analysis and studies. So as I mentioned, e-learning module is basically to learn. It explains the concepts. You cannot do anything else with that, but to learn. While the part simulators, which are the graphic user interface software based, we can use them for some analysis and will be good tools for the students.
Not only the most
and some music is coming. So that will be launched by us in the second half of this year. With this, I would like to conclude this session and call for the 15 minutes break. And then in 15 minutes, which is 11:15 Toronto time, we will start our next session, which is a panel discussion. Okay, so here is our second session today. So we are starting with our panel. And I will first introduce our panelists. So panelists, please, you are very welcome to turn your cameras on, but to stay muted. And as soon as I ask you to answer the question, you would be kindly asked to unmute and answer, but please keep your cameras on. So let me introduce first Aliki Van Heek. Since 2016, Aliki serves at the Unit Head 3E Analysis, Energy Economics Environment. This is one of the two units within the Planning and Economic Studies section at the agency. Aliki is leading a team in supporting agency member states' understanding of nuclear energy technologies compatibility with national sustainable development objectives, and how it can contribute to socioeconomic development, climate change mitigation, and energy security of supply in today's rapidly changing energy systems with increasing shares of intermittent renewables. Welcome, Aliki. Our next panelist to be introduced is Francesco Ganda. Francesco is the technical lead for non-electric applications at the IAEA, with responsibilities in the area of nuclear desalination, hydrogen production, district heating, and industrial uses of nuclear heat. Prior to joining the agency, Francesco spent a decade in the United States National Laboratories, supporting the programmatic activities of the US Department of Energy in the areas of fuel cycles, with special focus on economics and neutronics analysis of nuclear fuel cycles and reactor designs. Megan Moore is coming from Canada. She worked for Canadian Nuclear Laboratories since 2013. She has been involved in numerous projects that have allowed her to develop an expertise in nuclear economics and integrated energy systems. Currently, Megan co-chairs the Economic Modeling and Working Group of the Generation 4 International Forum. She's also the acting program manager for the Advanced Reactors Doctorate at CNL, Canadian National Laboratories. Akira Tokuhiro is a professor at the Faculty of Energy Systems and Nuclear Science at Ontario Tech University in Canada. He completed his dean appointment in September 2021. Akira's research activities are across advanced nuclear reactor and energy systems, thermal hydraulics, safety, experiments and measurements, modeling and simulation, and energy analysis. Notably, he served on the American Nuclear Society President's Committee on the Fukushima accident and served as technical editor on a book on the accident On the Brink, the Inside Story of Fukushima Daiichi. Welcome to our four panelists. The floor is open for the questions. Once again, attendees, kindly type your questions in the Q&A window, not in the chat. I will start with some questions that already came in. So I will start with asking Aliki. How can a nuclear and renewables complement each other in the best way? Aliki.
Okay, thank you very much, Tatjana. Well, a feature of renewables, well, if we there are many renewable sources, of course, but when we simply talk about renewables, we usually think about solar and wind, which are intermittent sources and therefore need to be complemented in those periods that there's demand and there's no supply from that side. So that's where nuclear can come in. And then, of course, the debate starts: is nuclear flexible or not? And so what we can say to that is, technically speaking, nuclear reactors are very flexible. I mean, you can turn them down to so and so many milliwatt and then go up to so and so many megawatt, and then also with the various digit behind that decimal comma or point. So that is not the point. The point is more the steam engine that's behind it. That is more or less flexible, but and not flexible to like the nuclear reactor. And so this causes some issues that makes this flexibility feature different in various regulatory environments. So at the end, it is like the nuclear power plants can be flexible to substitute the intermittent renewables. So in this way, they can work together, but it would be good if for the real peak to have still additional other very fast reacting sources in your energy system. And this way, nuclear can substitute a lot of the renewables that are not available, but it's only these very short periods of time that are very fast changes required.
Thank you, Aliki. Now I have a question for Akira. So the question is as follows. With potential co-location of both SMRs or SMR and the hydrogen production plant nearby, what might be some of the challenges and milestones needed to make that happen, made it realized? Please.
Yeah, thank you very much, and happy to be on the panel here, and excellent presentations this morning. I think some of the answer to some of the question, if I understood it correctly, was touched upon. At a high level, I think getting to the end is very important, and the co-location of the small modular reactor or micro modular reactor and a hydrogen plant and other products beyond the electricity and thermal energy, that being permitted in any given country is getting to the end, realizing the plant, the co-location is important. The other thing that I'm now worried about is about the codes and standards. Codes and standards and the regulatory that needs to be on the same timeline as the vendors who represent the SMR vendors and the hydrogen technology or the hydrogen plant as well, companies, right? And right now we don't. I think this is a wonderful venue for the nuclear people to talk to the hydrogen technology people, and we need to talk a lot about the co-location of the plant. But at the same time, the nuclear side is there's always a regulatory body. So, and depending on the country, the regulatory body may depend on the ASME or CSA for Canada and the US standards. So the standards and the regulatory decision-making process needs to be on the same time scale as realizing the SMR and hydrogen co-location plant. So I'll give that as a partial answer. Thank you.
Thank you, Akira. Great. Okay, here is the question that comes for Megan. So Megan, what will be the greatest challenge in Canada achieving its clean energy goals, net zero electricity by 2035 and net zero energy by 2050?
So honestly, I think the biggest challenge is just the scale and the timeline that we need to do this by. Achieving net zero isn't going to be something that happens with small independent initiatives. It has to be a large coordinated effort. And it has to be an effort that we look at all aspects. So it's not just about technology development and construction. We also have to look at training, skill development, supply chain ramp up, the integration of the supply and demand centers like we heard earlier today, energy policies, and much more. And how this actually happens in Canada isn't all that straightforward. So there's different provincial and territorial energy systems that still need their autonomy to be able to optimize operations within that jurisdiction, but they also need to have federal policies that are really going to drive forward Canada's overarching goals. And this ends up to create a lot of moving parts and a lot of players that all really need to talk together and work together to achieve this overall goal.
Thank you, Megan. I have now a question for Francesco. Francesco, what do you see as the biggest hurdles to the deployment of hybrid energy systems? Please.
Okay, oh, thank you. This is a pretty good question, and I think we discussed some of those elements. We heard about some of those elements in the excellent presentations this morning. In fact, to a certain extent, it was pointed out by at least one or two people this morning already that we are already seeing some elements of hybrid energy system. It is all about finding synergisms between the various components. It's not about finding those components in isolation, but it's about looking at the entire system together. And we are looking already at parts of hybrid energy system in actual grids nowadays. We have, in fact, in many areas already high penetrations of renewables. We have storage, generally electrical storage. We have conventional generators. We have smart meters. So we have many of those elements already there. Now, the biggest part that is really missing, at least to a large extent, is probably the integration and use of heat. So that is probably, technically speaking, at least, the biggest obstacle to a rapid deployment. And there are a couple technical reasons why integrating heat is challenging, and practical reasons. Number one, you have often a mismatch between the capability of reactors to supply heat and the available the need for industrial customers. Usually, the demand for heat is relatively small compared to the heat supplied by large reactors. We are talking about typically less than a megawatt in many applications for many industries. Sometimes you're going to the megawatt demand, thermal. To go to hundreds of megawatts, there are very few customers that might need this type of intense heat demand. You talk about refineries, talk about steel manufacturing, perhaps, but it's not very frequent. So now the next question is, if you have only a limited demand for heat, how do you best supply that heat in practice? And transporting heat is very expensive. That's the key point. You have pipelines for transporting heat lose heat pretty quickly and can cost in the millions of dollars. So there are a couple solutions. One is obvious. It's SMRs. It's microreactors. We talked about it extensively this morning. You can match better the demand with the supply. And we are starting to see a lot of development in this space, practical developments, and that might be a partial solution, at least to this problem. The other potential solution is the industrial parks. So you might have clustering of users of heat, and in this way it becomes cheaper to transport heat to those distances. The match between the temperatures needed and the temperature supplied can be an issue, especially when we go to very high temperatures. But there are technologies to augment heat, and those tend to be a little more energy intensive. And I think there should be a lot of research that should go into that space, because then this would expand potentially really the potential application of nuclear energy to a whole host of new technologies. Another area that I think it's a little bit understudied is the possibility of using nuclear heat for cooling. And we have specific technologies for that, those absorption chillers. And I think I haven't seen a lot of literature on that. And I think that's a potential customer as well that is underappreciated. And there's a lot of need for refrigeration. Of course, it's not in the hundreds of megawatts of demand. Another issue that I see as a problem for or a hurdle for the deployment of hybrid energy system and the use of heat is the ownership structure of those cogeneration products. Like in some parts of the world, or many parts of the world, for example, I'm thinking desalination, desalinated water. It's in the portfolio of the things we look in our project on industrial heat and use of nuclear heat for beyond electricity. And it's a very important topic for sustainable development. So if we look at the typical ownership structure of water distribution, these are generally public utilities that are publicly owned. And if you are, let's say, a private company that wants to that has, let's say, excess heat and wants to use that heat to develop a desalination facility and then sell the water, it becomes very difficult. You can use your water for your own needs internally, but if you need to sell that water outside of your company in the network to customers, I think at this point in many jurisdictions it's quite challenging. The laws and the structure need to change. You cannot wheel water if you understand the term. There's technology for wheeling electricity now, so you essentially can transport electricity on the network of someone else and sell it to their customers, but it doesn't apply to water, for example, and so, or other products. And so this needs to be changed and looked at. This is another hurdle for the deployment of hybrid energy systems from the heat perspective.
Thank you very much, Francesco. Appreciate your very detailed and good answer. Let me follow up with the question now for Aliki. The question is, can hydrogen energy economically be available for public to replace the oil and gas? Aliki? I don't know if you have some issues on my side. Yes,
okay.
please.
So do you hear me now?
Yes.
Do you hear me
go
now?
ahead.
Yes, good. Yeah. I got twice the request to unmute. Okay, thank you. So yeah, basically this the answer on this question for the moment is pretty short. No, it's not competitive, and almost nowhere. Because where currently almost all hydrogen is produced by with fossil fuels, mainly gas, and for this is perfectly embedded in an infrastructure, and well, with the current availability of these fossil fuels, okay, I'm not counting on, not including the big increase of gas prices that we saw the last few months, and then nuclear is simply, for the moment, it's the bit of an issue that it's this competitivity. But if you look at the future, we can we have the climate change mitigation issue, which means that somehow, one way or the other, these use of fossil fuels to generate hydrogen has to be discouraged. It can be through carbon taxes, or just forbidding, or well, whatever. But and then if these are taken off the market, yeah, then the competitiveness picture looks quite different. And also it depends very much on the location of both the customer and the producer. So when the hydrogen has to be transported over a long distance from the nuclear power plant to the user, of course, that also adds to the price. However, if nuclear reactors can be erected dedicatedly close to these user centers, yeah, then of course it will help. So there are plenty of reasons this way to see that there's a lot of potential for hydrogen, nuclear hydrogen, to become competitive in the not all too distant future. So I think I leave it with that.
Thank you very much, Aleki. I have a similar question, but I would like to address this question to Akira. The question is, do you think that hydrogen can replace oil within 10 to 20 years from now?
Good question. I'm not sure that it's hard to give a magic answer here, but so first of all, I'm now thinking in terms of the transition, which may be to 2030 to get to a lower carbon economy, maybe 2030, 2035. And there's another related word called transformation, which goes all the way, which overlaps transition right now, but goes all the way to 2050 or beyond, maybe 2100. You know, transformation may include fusion energy, but transition is what is based on what we have and what we can use. As far as so I think some of the other questions and some of the presentations today, Francesco mentioned a lot of good things. We need to undo a lot of things because, for example, you may have a nuclear utility owner and operator limited by law to only producing electricity. And then, so that would be a problem. That would be a hurdle. So you certainly need to loosen those kinds of constraints to produce not only thermal energy, but to produce electricity and to produce hydrogen, right? So, and then another good point was the kind of the public versus the commercial focus. We're bootstrapping kind of the effort now. If you have hydrogen as a means of energy storage or energy product, you need to have the demand commercially, right? So that is needed. And I think, you know, regardless, the petrochemical industries will be producing hydrogen, but they certainly need to talk to the nuclear industry and the collaboration. And then, as we know in Canada, remote communities will have a different attribute or characteristic than large cities. So we often tend to talk about C40 cities or large cities, but almost every country has rural areas and remote communities. So especially in Canada. So microgrids and national grids are certainly going to be part of the picture. And if we convert to hydrogen, well, that demand, supply and demand, I think will be still hold valid. So the point is to get off the fossil fuels and convert to hydrogen. And in the transition, we're being tested in the next 5 years, next 10 years, 2030 to 2035, how much progress we can make to a lower carbon. And I won't get into the argument about lower carbon or net zero or zero carbon economies of scale, but those are, you know, three different definitions. So thank you.
Thank you very much, Akira. So here we are having questions coming in and we are sorting out. So I think this one would be probably for Francesco. Which will be better for energy transition to use? Hydrogen directly or to use hydrogen energy carriers such as ammonia?
Okay, this is a pretty good question. Now you go with the various energy carriers that you have available, and of course hydrogen has the problem of density. So in many applications, as pure as gas, in many applications, it's quite challenging to store a lot of hydrogen and use it for certain applications, especially in transportation. You talk about shipping and airplanes, and those are probably among the hardest to decarbonize in the whole picture of our energy infrastructure. And when you talk about those, of course, you cannot store enough hydrogen on an airplane directly, or it's going to be very challenging, and use it for transportation. So you can go with ammonia or other synthetic products. Now, one problem with ammonia, and that's probably underappreciated, and I don't want to spoil the party here, but generally speaking, you have emission of NOx, because you're going to have high temperature combustion of not only the hydrogen part, but your nitrogen is going to be there. And so that needs some specific catalysts and pretty high quality catalysts to abate those NOx. And I don't think this is a solved problem. So before we talk too much about ammonia, I think it's very important to understand that complexity and perhaps put a little more R&D in this space. Another thing that so there's advantages and disadvantages in both. I think with a good R&D program, the problem of the NOx as currently is with ammonia can be reduced. Another possibility is to go the conventional Fischer-Tropsch and introduce carbon into your mix in a neutral way. So you recapture it and then you refabricate it this way. So in this way you balance it out in a way, and in this way you actually can create conventional hydrocarbons, and you don't have the NOx problem that you might have with ammonia. Obviously, hydrogen has a certain round trip efficiency that is not tremendously high. And so electrification, where possible, is also a viable alternative. That's something that needs to be considered.
Thank you very much, Francesco. So here is a question for Aliki. Aliki, the question is a little bit long, and I'm going to read it slowly. So nuclear flexibility is limited due to technical and safety issues, such as xenon oscillations, poisoning effects of work, but also due to economics. Generally, in common energy systems with increased share of variable renewable energy systems, nuclear has to support the penalties of load following. But these variations are mainly generated by the intermittency of renewable systems. Do you consider a common policy for low carbon energies? They mean nuclear plus renewables, with common advantages and drawbacks, will be an important step to go further with decarbonization policy. Please.
Do you hear me now? Good. All right. Yeah, thanks for the question. It's clear. There's an energy system, and there's both renewables that are intermittent and nuclear that is not. Theoretically, it could complement, but yeah, limitedly flexible. So in practice, what would you need, and that's what I would expect on a maybe longer term, some policy that is encouraging decarbonization, but then not only with these two sources, but also storage as an important third component. And hydrogen could play an important role in that storage as the storage medium. That's again depending on the location, the geography, hydropower in storage. That is also, pumped hydropower is also another option for low carbon storage. So I think that is an important third component. And then there's still, personally, I don't like it so much, but I think also some decarbonization policies will go into the direction of allowing carbon capture and sequestration into the system. So still allowing gas, but then still trying to capture the CO2 that is coming out of it. Of course, we know that this is not really super effective when you really talk about deep decarbonization, but at least as a kind of bridging, it could be still allowed, or because of some political and industrial interest, even be encouraged. I think I leave it that way.
Thank you. Would any other of panelists would like to add to this question? I can't see any hands, so if you would like to speak, just unmute. Aliki, you can mute back yourself and please unmute and comment. Okay, I don't see anyone, all right. So I have one question for Megan now. So Megan, what is the role for modeling versus demonstration of integrated nuclear energy systems?
So there's
The
a lot
topic
to
we did
unpack.
not really tap in.
Yeah, there's
What
a
is
lot to
the,
unpack there. So modeling and demonstration, and I would probably add experimentation to that list. They all need to work together to get nuclear energy systems to a point that they can actually be deployed in a community. So we've got things like systems modeling that's going to help us focus efforts on areas with greatest impact, helping to identify how to leverage the benefits of all these different technologies to work together in that overall system. Additionally, modeling paired with that experimentation needed to identify and address technical challenges. And then there's demonstration, which, yes, can be used to help with those technical challenges. But I actually think the biggest benefit to demonstration is going to be the ability to create social license. So demonstrations will answer some of those first of a kind regulatory questions. And they'll also provide communities an opportunity to come and kick the tires, so to speak, really see an integrated energy system and understand it a little bit better before making that choice to deploy it in their own community. So these are areas that CNL is working a lot in. Jan's presentation tomorrow is going to highlight a lot of our technical work, but we're also working to establish a clean energy demonstration, innovation, and research park at Chalk River. We commonly refer to it as Cedar Park, and its goal and purpose is a demonstration platform for these low carbon integrated energy systems. Of course, it will help to address some of those technical and regulatory challenges, but I think the big benefit that's going to come from the Cedar Park is that ability to create social license, so we can see these systems deployed more widely in Canada.
Thank you, Megan. Here we have a question now for Francesco. Francesco, the question is as follows. Decentralized hydrogen production is promising to reduce the need for storage and distribution and improving hydrogen grid reliability. How do you see nuclear-based hydrogen or purple hydrogen compared to green hydrogen from this point of view?
Okay, so this is an interesting question. Now, clearly, transportation of hydrogen is a problem that is not, I think, at this point, fully solved. We know it's a very, it's not dense, and when you don't have density, you have a high transportation cost. It's as simple as that. So there's various approaches, repurposing the conventional existing gas pipelines. It's not clear if this is feasible to 100% hydrogen, primarily because hydrogen is much smaller than CH4 and can leak much easier. So the existing CH4 infrastructure might not be able to carry 100% hydrogen, or probably it's almost sure that it cannot. So there are other techniques, such as, for example, remethanation. People are thinking of transforming the hydrogen back into CH4 and then putting it at this point into the pipelines. That's one technique. But clearly, this would be diminishing the efficiency of the whole process. Hydrogen produced at the point of consumption is what is done today, and it's clearly the most effective and cheap way of producing hydrogen because you avoid a transportation issue almost altogether. So that is clearly a possibility. In that case, it becomes obviously, as a consequence, challenging to make large amount of hydrogens in a concentrated spot using nuclear reactors. So you would have to essentially go the electricity route for the majority of the application in that case. As a practical matter, you would have to have electrolyzers at the point of consumption, gas stations, for example, if you are thinking of having cars, or industries where small amount of hydrogen is needed. You transport the electricity there, and then you make the hydrogen. That would be the way I see it, the practical way nuclear would work in this way, by making direct electricity and making the hydrogen at that. The other way, if you want to use purple hydrogen, I don't like the color purple, by the way. I think the others that have green and those colors are much better than our purple. I think we should try to change that color, but anyways, or pink even they call it. Anyways, if you try to use heat to make hydrogen, at that point, the fact that the possibility of using a nuclear reactor goes back to what I was discussing before. One is to essentially have large customers for hydrogen, refineries and other big consumers, or big synthetic fuel fabricators. And in that case, you can install a nuclear reactor there and use the heat. Or you can have industrial parks in which you share the heat between the hydrogen fabricator locally with a smaller footprint for hydrogen production, and have other customers for your heat that then can take the remaining heat from the nuclear reactor in an effective way. I hope this answered the question. Sorry for the long answer, but.
That's excellent. Thank you. Just a light comment. Purple color in many cultures is considered as a royal color. So if you consider nuclear to be in that level of technology development, maybe that was the reason for picking purple. All right. So I have a question for Akira. So where, for example, in the United States and in Canada, might potentially SMRs with co-located hydrogen plants might make the most sense, and for what technical and non-technical reasons, if you can comment that. Thank you.
Oh gosh, that's an interesting question. I think as I said before, we're in this transition to 2030, and as much progress as we can make to a lower carbon economy of scale is important. So and there are already ongoing activities, but I think some demonstration of an SMR plus hydrogen plus other technology plus storage would make the most sense, just as my humble opinion and a suggestion. So in thinking of North America, Canada, and the US, something on the West Coast, something on the East Coast, some essentially really the time zones, right? Something in the mountain states, something in the Great Plains, and maybe in the Gulf, right? Like Houston, Texas, it may make sense to co-locate an SMR and hydrogen, where you, I guess you have to reduce the cost. The cost is always a factor, and the workforce as well. To use as much of the existing infrastructure and the permits as possible. So it makes sense to take advantage of the petrochemical industries in Houston, for example, to have an SMR there producing hydrogen. You also need access. Going on some of the other things that presentations and what Francesco said, there is a natural gas pipeline map in the U.S., so it makes sense to have that nearby, right? So, and then you need to think in terms of a kind of holistic co-location of many things, all the way down to thermal and electrical demand or usage spectrum, so that you not only have the steel making or high industrial plants, but you also have other plants in businesses, commercial sector businesses that use the thermal grade lower grade, maybe thermal energies as well, so that you tap into the entire spectrum. So yeah, I think a select number beyond, you know, whatever the commercial market may demand, some demonstration co-located plants may be a good strategy to worldwide, not only in North America, but also worldwide. So thank you.
Thank you very much, Akira. Now we have a question for Megan. How such integrated energy systems can be of help to bring sustainability to northern communities in Canada? Megan.
So communities in the northern Canada are unique in Canada, but they do exist elsewhere, where the kind of geography you really can't connect them to any provincial national grids. And they can't even connect to other communities within the same territory because they're physically located reasonably far apart. So you end up with a lot of small individual communities, none of them having significant demand, and all of them having a hard time leveraging the more national level system. Resulting in a lot of them relying on diesel. Diesel energy is dense enough that can be shipped with there, but it creates very high costs. It's challenging to ship fuel there, and it costs to be done very frequently. So small modular reactors make sense to replace some of their electricity, but also that diesel is being used for heat in those communities. Some of them already have integrated district heating networks. So kind of the two easy ones are heat and electricity. Beyond that, there are opportunities that I think are still maybe a little bit farther along the time scale to look at application of hydrogen, being able to get some transportation, look at applications. I heard this morning about nuclear heat being able to help with food production. Another, just that it's challenging to transport diesel fuel, it's also challenging to transport food, fresh food. So there's a few other options that are long-term that maybe could be integrated into the system, but I think the near-term fix are the electricity and the heat for each of these small isolated communities.
Thank you, Megan. Now again, we have a question on hydrogen, so addressed to Francesco. What are the main problems which facing hydrogen production, especially in Middle East, and which is more easy, green or blue hydrogen? Now we have blue, please.
Okay, so I think there are a couple questions into this question. First of all, which one is more easy, green or blue? Well, okay, blue hydrogen is just for the benefit of everyone. Green hydrogen is intended the one that's produced with essentially electricity from the grid. Generally, it has to be carbon-free electricity and go to electrolyzers. The low temperature electrolyzers such as PEM, polymer electrolytic membranes, or alkaline electrolyzers. Blue hydrogen instead is using the conventional steam methane reformers, which is how hydrogen is done today. 95% of hydrogen is made with conventional steam methane reformers. And then adding on top of that, a carbon capture and sequestration facility to take that CO2 and put it somewhere or do something with it. So now, obviously, at this point, there has been a lot of talking about blue hydrogen. And from what I understand, it is not at this point a technology that is mature. It's not, certainly there has been a couple demonstration facilities in which people have demonstrated the capability to capture hydrogen after a steam methane reformer plant and store it somewhere. But I don't think it's a technology that's ready for large scale deployment and massive demonstration and rollout. I personally think that there are still issues that that needs to be resolved in terms of and discussed in terms of, for example, long-term sequestration of CO2. We have had decades of experience in licensing nuclear repositories. We haven't had decades of experience in licensing CO2 repositories, to my knowledge. So we've had accidents before in which CO2 leaked out of the ground, were natural formations. But to my understanding, I think it was in India, there was a massive CO2 leak from an underground natural formation, and it killed some people because of suffocation. So large storage of CO2, it's at this point something that probably needs to be licensed. Utilization of CO2 is certainly an option, but we need to keep in mind the scale of this problem. It's something that's the amounts of CO2 that you would have to utilize are beyond what at this point are the needs for CO2 in all the various industries we have. I lived for a while in the San Francisco Bay Area. We had a coupled hydrogen CO2 production facility. Chevron had a big refinery there, and they had a steam methane reformer plant for supplying the Richmond refinery, and then they piped the CO2 to a Coca-Cola plant, so it became CO2 for consumption. So that was a self-sustaining system in which the CO2 did not need to be stored. Now, if and when blue hydrogen will be at scale is something that at this point is not known. I will give a presentation tomorrow, and I'll show exactly something that goes along these lines. If if blue hydrogen is in fact technically feasible at very large scales, and it's proven that CO2 can be stored for geological times in formations without an issue, then it's a very competitive technology from a point of view of cost. However, one needs to keep in mind all the technological complexities, and another issue is the leaking of CO2 from CH4, sorry, from the pipelines, and especially the extraction sites, when we talk about massive deployment of blue hydrogen. I'd like to point that out here because this is something that's underappreciated. It's virtually impossible to extract gas without having leaks, at least with current technologies. Okay, I'm gonna pause here so that people can absorb this concept. Now, CH4 is a greenhouse gas that's much more powerful than CO2. We talk about orders of magnitude. And so at this point, if you factor in those leaks that you inevitably will have for the CH4 extraction, just extraction, you might have a much greater impact from blue hydrogen than what is normally quantified when people do the formal analysis. Secondly, you are going to have to transport that CH4 from the extraction site all the way to the plant where you essentially make the hydrogen. And that transportation in the current network infrastructure for CH4 has leaks. Okay, it's not enormous leaks. It depends on the age of the infrastructure. In the US, I think it's more leaky than in Europe, but because the infrastructure is older. But you still have leaks. And so that impact on greenhouse gases and global warming needs to be quantified, needs to be included in the analysis. Okay, so at this point, certainly blue hydrogen might have a role to play. I don't know if you do an analysis and base it only on cost, and you make optimistic assumption on the technical feasibility of this technology, and you avoid including the leaks, and you assume optimistically that you can capture 90% of your CO2 emitted from the process, then yes, that is a very competitive technology. But let's keep in mind another issue. When we do an analysis and we look at the hybrid energy system, which is the topic of today, there are synergisms there. And you need to, when you do actually a cost analysis, you don't find the technology that wins everything. You're going to have a mix of technology in the lowest cost system. And your mix of technology will include green hydrogen and blue hydrogen and purple hydrogen. Okay, it will include everything in the spectrum, because you are going to capture the synergism of all the various technologies, And so your lowest cost mix will have a little bit of everything.
Thank you, Francesco, very much. Before I move to the next question, actually, there is a question to clarify terminology. What is the difference between the hybrid energy system and integrated energy system? Is it the same or there is a difference? So who would like to address that question? Akira, would you like to address the question?
Well, I can give you a short answer. I think to me, I was thinking there's not a difference between the for me, between the hybrid and the integrated. I suppose a little bit of semantics. I think there's a bit of an inference that the integrated is part of when you design an integrated system, it's the integration of the components and the pieces, subsystems, starts at the very beginning, and that may be also for a hybrid. But yeah, I think there's very little difference between, for me at least, very little difference between hybrid and integrated. It's a good point that we should not confuse. If there is a difference, we should define it. If there's not a difference, we should also say that they're identical and can be interchanged. Yeah, so thank you.
Thank you. I would like to ask also Francesco to comment on this question, please.
I was hoping to avoid it because I'm not sure what's the difference myself. I think people use those interchangeably. My intuition is that it also changes based on geographical location. I think the terminology in the US, the preferred terminology seems to be hybrid energy systems. I've seen in other areas talking about integrated energy systems. And so probably actually these types of forums is a good occasion to bring all the stakeholders together and have a little bit of a better defined terminology. So I personally would avoid claiming any difference between those two. I agree with Akira, but I might be wrong. So on that I seriously don't know.
Thank you very much. Megan, what do you think? Is that just semantics, or there is a difference from technology point of view? How Canada looks into this?
I agree with Francesco. They're, at least in forms of this where it's conversational, they're definitely used interchangeably. And when it comes to more written and published work, it does seem to vary more by geography than by exactly what they're defining, which term is used.
Thank you. Aliki, what is your viewpoint on hybrid versus integrated energy systems?
Yeah, I agree with Akira, Francesco. Basically, I don't see so much difference. It's a semantic thing. You can call it the one way or the other. Basically, the important thing is more not whether to talk about hybrid, non-hybrid, integrated, non-integrated systems, because in practice, almost all energy systems are integrated or are hybrid. The important thing comes in when you start to optimize hybrid systems or integrated systems by not only connecting them with by electricity lines, but also by kinds of heat transport or pipes or synthetic fuels, hydrogen, these kind of things. But the basic electricity system in almost any country is already hybrid. There are several energy technologies present on the grid, and whether you call that integrated or hybrid doesn't matter so much, but also it matters the most what you do more than just generating electricity.
Thank you. I think Akira raised the hand.
Yeah, it's a very good question, and I think Francesco and Megan also, and Aliki, it's this type of forum where we maybe need to discuss and come to an agreement that there's no difference between integrated and hybrid. just my comment is that we also have to take in mind the world that we live in, which is, alluding to social media. So it may be important to the hashtag integrated, hashtag hybrid, that there's not a difference, so that we don't generate confusion in the public domain, right? So that may be also an important factor. So just wanted to add that. Thank you.
Thank you very much. Okay. Now, there is one question that is very interesting. I would like also Akira, if you don't mind, to address. How to balance the safe distance of nuclear power from the end users of hydrogen nearby?
Oh, yeah, that's an interesting question. It has, standards and regulatory impact. So my ongoing thinking, my current thinking is that the nuclear power plants all over the world, whether they're and for some time to come, because it's important that it's in a regulated space. So, and safety is, in a very simple terms, safety is number one. So anything that you put around the nuclear power plant, the small modular reactor or micro modular reactor, cannot, I think it's reasonable to say that you cannot impinge, you cannot encroach on the safety standards of the new operations and maintenance and so forth in security of the nuclear power plant. The other things that are around it, the hydrogen plant and other storage and so forth, may be regulated, but and the nuclear regulator may have some say. But I think that if you can write anything in stone or concrete, you can say that the safety standard cannot be violated, right? So what that means is that nowadays there's a technical basis on, for example, the emergency planning zone or exclusion zone. What is the, just 5 seconds, what is the source term and what can happen, and what are the consequences? So whatever you put around it, you want it to be small, because I was thinking, Professor Dincer's presentation, when you put a hydrogen plant 10 kilometers away from the nuclear plant, then you're going to have losses. So you want to put it as close to the nuclear power plant as possible to avoid those losses in terms of the electricity or the heat, especially heat, thermal energy. But then you have to think of some innovative regulatory and standards to go along with it, so that that integrated thinking is the losses and the availability and the response to the supply and demand of the market, commercial market, is addressed as well. So I would say the nuclear plant has to have a technical basis, and that you cannot encroach on the safety standards of the nuclear plant. But everything around it has constraints, but they are different constraints. Thank you.
Thank you very much. And maybe a follow-up question, also it's addressed to you, Akira. Do you think pursuing such integration of the system, nuclear and renewables, in tightly coupled designs can jeopardize the safety of the nuclear power plant?
Yeah, so just a little bit more detail, because I often think about this in terms of AI and ML of the plant. The safety of the primary system is you cannot have a tightly coupled system unless you have other means like thermal storage or electrical storage, where you have the flexibility integrated into the design. So otherwise, but the primary system is you cannot. There have been examples of seasonal load following using nuclear power plants, like in France. But if it's too tightly coupled, you can get yourself into a situation where if something happens, then it can you cannot have it to impede or disrupt the primary system safety. So this is a good question, and I think this is why you need good computational modeling, because you can consider many more options and scenarios with a computational model than with a demonstration plan. So thank you for that.
Francesco, please.
Okay, thank you, Tatjana. I just wanted to add one little thing, that this is a major issue for obviously for those type of systems, and so we are at the agency are going to start an activity. We actually already started with a technical meeting last year before I joined in this position on the safety and the licensability of cogeneration systems, and we are going to have activities follow up on that. So we are going to have, we're going to send out requests for member states to participate in technical meeting, consultancy, and so on. Jointly with the safety part of the agency, we are engaging the external event safety section to essentially help us look into those issues. So stay tuned.
Thank you, Francesco. Great point. So here is the question for all of you. So the question is, how do you see the role of artificial intelligence in facilitating the implementation and deployment of integrated energy systems? Agency is becoming very active in understanding the role of artificial intelligence in many fields. So who would like to start, please?
I can, this is Akira, I can give my 2 cents worth on, because I mentioned artificial intelligence and machine learning. Again, you cannot really touch, I think in terms of safety, to maintain the safety, you cannot touch the primary system of the reactor. Now, when you talk about artificial intelligence and machine learning, you have to also talk at the same time. I think it's really important to talk about data quality and the data standards, because you always have with these kinds of artificial intelligence and machine learning or neural methods, you have a learning set and then a training set and so forth. So you have to think about the data quality, things that are away from the primary system and where that happen routinely every day, maybe good for AI or machine learning. So for auxiliary systems that do not impact safety, it may be good, but certainly not good for one-off events, because then it can add bias into the AI and the data set. So I'll just stop there, but I hope to hear some other comments from the other panelists. Thank you.
Thank you, Akira. Who would like to go next? Francesco, would you like to provide some input?
Of course, yeah. I can also offer my 2 cents, like Akira. So one area that I think could be exploited effectively is massive optimization. So here you have, at this point, optimizers are limited to a few billion variables. When you start looking at, so essentially, when you do simulations for or optimization for your integrated energy systems, you're looking at clustering similar generation technologies. You're looking at simplification, such as, for example, avoiding the transportation network in there, so the transmission grid, and so on. So you avoid individual storage facilities with their connection. Now, if you start looking at those more advanced computational methods, you might be able to do optimization of more complex system by orders of magnitude. And I'm also thinking quantum computing that might also help in that direction, because really the complexity of the most complicated, of the most advanced solvers really limits itself to a couple billion variables, to my knowledge. I think the best commercial solvers essentially stuck there. So you cannot look at individual facilities. You cannot optimize national or regional grids at the sufficiently detailed level to have both the facility storage and transmission networks at this point at the same time. So that's, I think, an area where we could actually benefit from that.
Thank you very much. Anyone else would like to add to that question? All right, then I do have a question for Aliki. Some see the current energy system in countries with nuclear and renewables already as hybrid energy systems, grid systems where renewables and nuclear are coexisting. Do you agree? Why or why not?
Okay, yeah, thank you. Well, that's what I indicated before, that if you see a hybrid system is already an electricity grid system where multiple technologies are contributing, including nuclear and renewables, yeah, then you're already done, and then there's nothing new about that. I think we should be careful with expressing ourselves and using the words or propagating the definition properly, really communicating what we mean with hybrid systems, that it's really going beyond what there is already. Otherwise, it's not interesting, and it's not clear that there still needs to be something optimized, and or at least something to be won. And so I think we should be very clear that the current electricity system are well, not hybrid at all, or you can even say, okay, loosely hybrid, loosely coupled hybrid. That's more the official, but yeah, then you have to explain that, and then you're already losing your audience. But just make clear, it's not only electricity, it's also other forms of energy that are being exchanged from the producer to the consumer, and the whole system being optimized to that. So it's including not only electricity, but also the synthetic fuels, also the hydrogen, also the heat in its various forms. So that's how I would answer this question.
Thank you very much. We have a question for Francesco. Is methane pyrolysis, plasma molten metal, and thermal gas a potential good option to produce blue hydrogen? Because it also produces high value products such carbon black. What do you think?
So can you reread it? I understood is pyrolysis. Can you kindly reread it, please, Tatjana?
Is methane pyrolysis, like plasma, molten metal, and thermal gas, a potential good option to produce blue hydrogen, as it also produces a further high value products such as carbon black? What do you think?
So that's a very technical question, and I don't know if I'm fully qualified to answer this, because it's really a petrochemical engineering almost type of question. The pyrolysis technology, I think it's driven by very, very high temperature gases, and so this would be a little bit outside of the realm of what we can really do with nuclear at this point. It's not really anything that could be done with nuclear. For blue hydrogen, yes, you definitely can have, there are processes that, that are trying to do this. I'm not sure whether this is a viable technology or a competitive technology as compared to the conventional steam methane reformers that it's used currently. So this is something that I don't know the latest development. I know, I would guess that if it was a mature technology at this point, more refiners and others would actually use it and think of implementing it in refineries, while in practice, many are actually looking at the option of other methods for hydrogen generation, such as, for example, nuclear, in order to reduce their carbon footprint and be more compliant with the national targets in terms of CO2 emissions. So that would be my 2 cents, but I don't think I'm fully qualified to answer those petrochemical engineering questions.
Thank you, Francesco. I think this is sufficiently good to provide some guidelines for looking further into it. There is also one question that is interesting, and I will give a panel to volunteer to address. We are coming close to finishing the panel session. How is it possible to use plasma technology in energy transition? Who would like to give us? Akira, maybe we start with you.
I can give you maybe a partial answer. I mean, the easy answer is certainly technically possible to use plasma technology for nuclear, but will it be adopted in the commercial space, and will it be scalable enough to be widely used? So that's a simple answer. You know, of course, you know, you can, with the plasma, you can probably do, and there have been concepts of fuel enrichment using plasmas, but yeah, is it widely used as opposed to a diffusion method in fuel processing? It's another matter. So I think there's always an interesting technical conversations, but I said at the very beginning, getting to the end for me right now is very important in the transition. So although research is important, it has a different time scale, maybe have, you know, a longer time scale in transformation. So I think we need to keep the option open, and so some level of activity on how plasmas can be used in the nuclear domain that needs to be maintained, but so that we have the option maybe 15 and 20 years from now. But that's all I had to say about that. Not specifically about the technology. Thank you.
Thank you very much. Anyone would like to address the question? It is probably for quite different department rather than us here. Okay, there is a last question.
Okay.
Yes, please, Aliki, go ahead.
Okay. Okay. Yeah. So with plasma technology, if you mean nuclear fusion, I think that is what is meant. Well, we have to be clear that we are not succeeding yet with this machine ongoing, whether it's the one plasma technology or the other one. However, we can observe that, especially in the last few years, there are multiple startups, really some tens have been founded with various intellectual property on this various types of plasma technology. They are attracting a lot of investment compared to at least efficient startups, and interestingly, they are developing or attracting investments to develop this technology, although in multiple cases it's not even clear what the technology is. So we cannot say nuclear fusion is only ITER and it's big and probably doesn't fit the market. That there are multiple initiatives with adjacent plasma technologies that are smaller scale, and yeah, we have just have to wait and see how which ones of these, if at all, can penetrate the market. But it's an interesting development. Just I wanted to add.
Thank you very much. And then we will be closing with the last question that is addressed to me because they ask if the agency conducts training sessions and activities on the use of e-learning tools that I presented, e-learning modules and other tools. And as I mentioned, all these tools are available for free to our member states. They need to just follow instructions on our webpage is how to ask for. And of course, we conduct training sessions and activities. Now everything is virtual still. And also there is a protocol and a procedure. So in any case, if I receive any request, I will provide inputs on how and guide on how to move forward. With this, I would like to thank our panel members, Megan, Francesco, Aliki, and Akira, for your great contribution, for your time, and for sharing your extensive knowledge and expertise in the field. And with all your agreements, I would like to close the session and call it successful. We are continuing tomorrow as per the agenda at 9 o'clock Ontario Tech Time.
Thank you very much, Tatjana. I would like to extend a thank you to all speakers and panelists of today's session. And a special thank you goes to Tatjana for sharing today's sessions. I would like also to extend a thank you to over 650 participants who have registered to join us today. Today's session is being recorded, and a link of the recording will be sent to all who have registered in this event. Please remember that the event continues tomorrow at 9 a.m. Toronto's time, and I hope to see you all back here tomorrow. Wishing you all the best today. Have a wonderful day. Bye-bye.